in just 3 days, on December 19th, Unveiling. Something from beyond our solar system will make its closest approach to Earth. This is not merely an ordinary event, it's the arrival of an interstellar object that has been traveling for billions of years across the cold expanse of space. And in the last 72 hours, something extraordinary has occurred. For the third time, this object has shifted color. First, it gleamed a deep, foreboding red. Then, it turned an eerie, almost otherworldly green. And now, as astronomers from around the globe confirm, this enigmatic visitor, known as 3I Atlas, is transitioning to a brilliant, unsettling gold. This color shift is not just a trivial detail, it's a signal that has been observed before. The last time a comet exhibited such a transformation, it fragmented into pieces shortly after. The scientific community is now gripped with a burning question: is 3I Atlas on the verge of breaking apart before our very eyes? Or is something more profound occurring, something that defies our current understanding of the cosmos? Tonight, we will delve deep into the mystery, examining every clue, every anomaly, and every theory from the most grounded to the most extraordinary. By the end of this journey, you will understand why over 80 astronomers from the United Nations International Asteroid Warning Network are keeping a watchful eye on this object around the clock. Why the anti-tail of 3I Atlas has grown to an astonishing length, now extending farther than the distance from the Earth to the Moon, and why many scientists believe that 3I Atlas is not behaving like any comet we've encountered before, challenging everything we thought we knew about these icy wanderers. Stay with me until the very end, because what happens in the next 72 hours could rewrite everything we thought we knew about visitors from beyond our solar system. But before we dive deeper, a quick reminder to like this video. And if you're intrigued by the mysteries of the universe, don't forget to subscribe and hit that notification bell so you'll never miss an update. Let's begin with what has transpired over the past 72 hours, because the timing is nothing short of extraordinary. On December 10th, Unveiling, an amateur astronomer named Alberto Quano Vodner captured an image of 3I Atlas that immediately sent ripples through the astronomical community. For months, this mysterious object had been glowing an eerie green since emerging from behind the sun in November. But what he captured on that fateful day was something unexpected, a golden hue. Initially, some dismissed this golden transformation as an artifact, perhaps a glitch caused by the imaging equipment, or maybe atmospheric distortion. But then, more and more observations poured in. On December 13th, Tony Scamato from Calabria, Italy, using a 0.25-centimeter telescope, confirmed the golden glow. By December 14th, Dan Bartlett in California, armed with a larger 14-inch telescope, also captured the same golden hue. The evidence was undeniable. 3I Atlas was changing color from green to gold. Pause for a moment and reflect on the significance of this. An object that has traveled for perhaps 7 to 14 billion years, originating from another star system, is now transforming its appearance in real time as we watch, a relic from the distant past, shaped by the cold expanse of interstellar space, now turning before our eyes, revealing its true nature. But this isn't the first time we've witnessed a transformation like this. When 3I Atlas was first detected on July 1st, Unveiling by the Atlas Survey Telescope in Chile, it presented with a deep, blood-red hue. This red coloration was attributed to organic compounds, complex carbon-based molecules gathered from its long journey through the cosmos. These compounds were formed from remnants of exploded stars and cosmic dust scattered across the vast void between stellar systems. The intensity of the red was so profound that astronomers noted it was darker and more vibrant than the colors of previous interstellar visitors, like 1I Oumuamua and 2I Borisov. This redness suggested that 3I Atlas had been absorbing materials from interstellar space for eons, a cosmic scavenger accumulating remnants from supernovae, nebulae, and the very fabric of the universe itself. But when September arrived, everything changed. As 3I, Atlas, crossed the critical threshold of 5 astronomical units from the Sun, the waterline, in cometary terms, everything about this object shifted. Water ice began to sublimate, and the coma, the envelope of gas and dust surrounding the nucleus, erupted with activity. The once vibrant red glow faded, giving way to a brilliant green. This green glow is well understood in cometary science. It's a signature of diatomic carbon molecules, 2 carbon atoms bonded together. When solar ultraviolet radiation strikes these molecules, they become excited, emitting light at wavelengths our eyes interpret as green. This color has been seen in many comets before, such as the famous Comet 12P, Pons-Brooks, during its 2024 flyby. It's a hallmark of an active comet. But gold is rare. Gold is unsettling. To understand the significance of the gold, let's look at another comet. In October 2025, Comet C 2025 K1 Atlas, a relative of 3I, Atlas made an extremely close approach to the Sun. It flew within 50 million kilometers of our star, 4 times closer than 3I, Atlas did during its own perihelion. Many astronomers expected K1 to be torn apart by the intense heat and gravitational stress, but it survived. And when it emerged from the Sun's glare, it was glowing gold. The astronomer Dan Bartlett, the same one who photographed 3I, Atlas, in its golden phase, captured K1 in late October. The comet displayed a stunning red, brown, and gold color, rare in comets and visually striking. But even more intriguing was the spectroscopic data from astronomer David Schleicher, which revealed an unexpected lack of carbon-bearing molecules like dicarbon, carbon monoxide, and cyanide. This depletion in carbon compounds was so extreme that it's only been observed in 2 other comets in history. And just days later, K1 began to fragment. By November 11th, telescopic observations confirmed that K1 had broken into at least 3 pieces. The golden color, it seemed, was a warning sign, signaling that the comet's internal chemistry was destabilizing. The volatile ices that had bound its nucleus together were being exhausted. The end was near. Now, 3I, Atlas, is following a remarkably similar pattern. First, red to green, and now, gold. And it's doing so while moving into the same region of the sky as K1 into the constellation Leo. The lion, a symbol historically associated with royalty and power. The coincidence has not been lost on observers, though we must be cautious in not conflating poetic symbolism with scientific analysis. From a chemical standpoint, the gold color suggests that 3I, Atlas, has burned through its reservoir of carbon compounds during its approach to the Sun. The intense solar radiation has stripped away the volatile gases that had been producing the green glow. What's left is a coma dominated by dust particles, reflecting sunlight in warmer wavelengths, rather than emitting the characteristic green of excited carbon molecules. Essentially, 3I, Atlas, may be exhausted. The organic materials that gave it its red hue, the volatile ices that powered its green phase, these may all be depleted. What we are witnessing now might be the bare remnants of a once vibrant interstellar traveler, its treasures stripped away by its close encounter with our Sun. But here's where things get complicated. If 3I, Atlas, has lost most of its volatile material, then we should be seeing a decrease in its activity. Its coma should be fading. Its brightness should be diminishing. Yet, while it has indeed dimmed somewhat since its peak, it remains remarkably active. Images from December 14th and 15th show not just the golden coma, but something else, a prominent antitail. This antitail is not a trivial feature. It extends an astonishing 500,000 kilometers from the nucleus of 3I, Atlas, larger than the distance between the Earth and the Moon. This is material streaming from the comet in a direction that should be impossible under normal circumstances. Solar radiation pressure always pushes cometary material away from the Sun, sculpting the characteristic tails we know so well. Yet, 3I, Atlas, is defying this basic law of cometary science. Its antitail is not pointing away from the Sun. but directly toward it. Harvard astrophysicist Avi Loeb has been tracking this anomaly since July and has noted that, for the material to extend this far, it must be moving toward the Sun at speeds exceeding 130 meters per second. The mechanisms behind this strange behavior remain unclear, but the idea of a technological thruster, though controversial, has been proposed. Loeb, however, is not the only one to suggest an unconventional explanation. The anti-tail could be composed of large particles that are resistant to being pushed backward by solar radiation pressure. Alternatively, it could point to something much more extraordinary, something that could challenge our understanding of comets themselves. While skeptics argue that 3I Atlas is still behaving like a comet, albeit an unusual one, there's no denying that it's not following the typical patterns we've observed in solar system comets. The persistence of the anti-tail, from pre-perihelion observations in July to its current size, continues to confound our expectations. The anti-tail of 3I Atlas is not just a temporary effect. It is a physical feature of the object itself. But what is powering it? Where is the energy coming from? What is driving the material to move toward the Sun at such remarkable speeds in just 3 days? On December 19th, 3I Atlas will make its closest approach to Earth, at a distance of approximately 270 million kilometers. This is our best opportunity to study this object before it begins its long journey toward Jupiter and beyond. Never to return. The answers we uncover in the next few days may change everything we thought we knew about the objects from beyond our solar system. As Lowe himself has emphasized, December 19th presents a unique opportunity, an ideal moment for Earth-based telescopes to observe 3I Atlas as it makes its closest approach to Earth. The James Webb Space Telescope, the most powerful tool humanity has ever built for studying distant celestial objects, is poised to make fresh observations this December. Meanwhile, the Hubble Space Telescope has already provided invaluable images, including a post-perihelion view from November 30th, which clearly showcases the teardrop-shaped coma and the intriguing sunward extension, leaving us with far more questions than answers. Ground-based observatories from all over the world, Chile, Hawaii, Thailand, Italy, are focused on this object every clear night, their instruments trained on the shifting Golden Enigma of 3I, ATLS. What they uncover in the coming days could answer the burning question hanging over this comet: is 3I Atlas truly fragmenting, with its golden hue heralding the end of its journey, just as it did for Comet K1 Atlas? Or could we be on the verge of discovering something entirely unprecedented, something that challenges our fundamental understanding of interstellar objects? There is, however, another possibility, one that has not yet been fully considered. What if the gold isn't a sign of death, but a sign of revelation? What if the stripping away of volatile gases is not a precursor to destruction, but rather the unveiling of something hidden beneath its surface, something ancient and profound, something that has been accumulating for billions of years on its journey through the cosmos? What if, as it reveals more of itself, 3I Atlas offers us a glimpse into a composition that defies everything we thought we knew? Spectroscopic analysis of 3I Atlas has already revealed startling clues: nickel emissions without corresponding iron, an anomaly in the typical chemistry we observe in solar system comets. This discovery alone defies our expectations, suggesting that this object may possess a composition unlike any comet we have ever studied. Further analysis has shown that its surface exhibits signs of radiation damage extending 20 meters deep, an indication that it has been exposed to cosmic rays over time periods far exceeding the age of our solar system. And its trajectory, which aligns within a mere 5 degrees of the ecliptic plane of our solar system, is another anomaly. Statistically speaking, this is a coincidence with only a 0.2% probability. These facts alone suggest that 3I Atlas is no ordinary comet, but rather something entirely unique in its origin and composition. With just 72 hours remaining until its closest approach, we find ourselves standing on the edge of an unparalleled opportunity to study this interstellar visitor before it begins its long journey toward Jupiter and beyond. Destined never to return, the transformation of 3I Atlas into its golden phase may be its final metamorphosis, but could it also be the beginning of something much deeper? What truths lie beneath its mysterious surface? What secrets could this ancient traveler told? And how might our understanding of the cosmos be reshaped by the answers we uncover? Or perhaps the gold is only the beginning of the true mystery. As we will explore in the next chapter, 3I, Atlas, continues to present us with more puzzles than we can solve. From the bizarre anti-tail to a sunward jet that defies the known rules of cometary behavior. In cometary science, there is a long-held rule that material ejected from a comet always flows away from the sun. The mechanism behind this is simple and elegant. Solar radiation exerts pressure on the particles streaming from the comet's nucleus, pushing them backward, shaping the iconic tails that we have all come to recognize. The ion tail, composed of charged particles, always points directly away from the sun, driven by the solar wind. Meanwhile, the dust tail curves gently, its trajectory a delicate balance between the comet's forward motion and the relentless push of sunlight. But every comet we've studied until now shares one essential characteristic: their tails always point away from the sun. 3, Atlas, however, seems to have missed that memo. Since the first high-resolution image of the object was captured by the Hubble Space Telescope on July 21st of this year, 3I Atlas has been displaying a feature that should not exist: an anti-tail, a coherent stream of material extending directly toward the sun. In the initial Hubble image, the coma was teardrop-shaped, with its elongation pointing toward the sun, which defies the models we've relied on for so long. At first, some astronomers speculated that this could simply be a temporary perspective effect, a geometric artifact that would resolve itself as Earth's position relative to the comet shifted. This type of explanation has worked for solar system comets in the past. When Earth crosses a comet's orbital plane, the viewing angle can create the illusion of a sunward extension, even if the material is actually moving in the expected direction. But 3I Atlas has stubbornly refused to follow this logic. The sunward feature has persisted through August. It remained through September. It was still there when the object emerged from solar conjunction in November. And by December 15th, the anti-tail had not only persisted, but had grown to extraordinary dimensions. To put things in perspective, the anti-tail of 3I Atlas now stretches an astonishing 500,000 kilometers, 500,000 kilometers of material streaming directly toward the sun. For context, that is a greater distance than the average distance from Earth to the Moon. In fact, the anti-tail is now so vast that you could fit the entire Earth-Moon system inside this structure, with plenty of room to spare. This is an order of magnitude greater than what we've ever seen in a comet before. The latest images from amateur astronomers around the world confirm the findings of professional observatories. In Thailand, astronomer Tia Sakalawan captured the object on December 13th using a modest 0.2 telescope. The processed image shows the unmistakable sunward extension of the anti-tail. Meanwhile, Dan Bartlett, using a larger 14-inch telescope in California on December 14th, not only captured the anti-tail, but also noted a distinct green-blue coloration in the sunward extension, suggesting active emission processes are occurring within this impossible structure. How do we explain material streaming toward the sun when every force we understand should be pushing it away? 3 scientific papers have attempted to address this question, each offering unique insights that highlight just how far outside the realm of normal cometary behavior 3I Atlas is pushing our understanding. The first 2 papers, co-authored by Avi Loeb and Eric Cato, propose that the anti-tail consists of ice fragments shed from the sun-facing side of the nucleus. These fragments, they argue, are small enough to sublimate rapidly, but large enough to resist being pushed backward by radiation pressure during their brief existence. As they evaporate, they create the appearance of a sunward stream of material. While this explanation is clever and fits within known physics, it requires some fine-tuning of particle sizes and sublimation rates. The third paper, published by Loeb alone on December 8th, offers a more provocative hypothesis. What if the anti-tail is not composed of ice fragments at all, but instead represents a swarm of solid objects that lag behind 3I, Atlas, due to non-gravitational acceleration? This scenario would suggest that 3I, Atlas, is being pushed outward by a force beyond solar gravity and radiation pressure, while the objects in its wake, not experiencing this additional acceleration, appear to fall behind, creating the sunward anti-tail. The evidence for this non-gravitational acceleration comes from tracking data provided by the Jet Propulsion Laboratory's Horizon system. Since November, the orbital solutions for 3I, Atlas, have required the inclusion of a tiny, but measurable, acceleration component that behaves in a manner akin to solar gravity itself. This acceleration is small, approximately 2% of the gravitational acceleration, but it is persistent and undeniably real. Something is pushing 3I, Atlas, in a way that cannot be explained by gravity alone. For most comets, non-gravitational acceleration is attributed to outgassing, where escaping gas acts like a tiny rocket thruster, nudging the nucleus in the opposite direction. However, the amount of outgassing required to explain 3I, Atlas's observed acceleration, is enormous. Calculations suggest that 3I, Atlas, would need to be losing mass at an astounding rate of 2 million kilograms per second at perihelion 2.000 metric tons of material every single second. If this mass loss were truly occurring, we should be seeing significant evidence of it, an expanding cloud of gas detectable through spectroscopy, dramatic brightening events as fresh material is exposed. But what we actually observe is something far more peculiar. The coma of 3I, Atlas, remains relatively compact, and its bizarre sunward anti-tail continues to defy any easy explanation. Even the Hubble Space Telescope's high-resolution images, taken on November 30th, provide the highest clarity we've seen of this anti-tail, leaving us with more questions than ever. These images, captured using the f350 LP filter aboard the Wide-Field Camera 3, show that the coma is anything but chaotic. In fact, it's almost perfectly spherical, an almost symmetrical glow extending 40,000 kilometers in every direction from the central condensation. This observation, so different from the typical messy, asymmetric comas of comets, is another mystery waiting to be solved. What exactly are we seeing here? What does this smooth, uniform structure tell us about the true nature of 3I, Atlas? Emerging from the spherical envelope of 3I, Atlas is the narrow, elongated anti-tail, a striking feature that has grown sharper and more defined with each observation. The word that continually surfaces in scientific discussions about this peculiar structure is coherent. The anti-tail remains remarkably coherent, holding its form over vast distances, hundreds of thousands of kilometers, without diffusing or scattering in the way that gas clouds or small dust particles typically would. This coherence makes it appear less like a random ejection of material and more like a directed, purposeful stream of matter. What force could be behind such a coherent structure? One possible explanation, favored by those seeking conventional answers, involves the unique geometry of 3I, Atlas itself. If the nucleus is highly elongated, with one end always pointed toward the sun, material could be expelled more efficiently in the sunward direction, maintaining a coherent structure as the comet rotates. The rotation would provide the necessary momentum, and the jet geometry would help explain the directional consistency. However, this explanation becomes complicated when considering the comet's measured rotation period of approximately 16 hours. Over the past 45 days since perihelion, the nucleus would have completed dozens of rotations, yet these jets have managed to maintain their linear configuration. If the jets were being expelled in a spiral pattern, as our models predict, the material would be more dispersed, not the tightly coherent structure we observe. Yet, the most recent images defy this expectation, showing tightly collimated jets extending over distances greater than 1 million kilometers, maintaining their orientation across multiple observations. This persistence is what Avilo has termed the 12th anomaly of 3I, Atlas. a striking feature that sets this comet apart from all others we've studied. Let's take a moment to appreciate what we're witnessing here: a celestial object from another star system, traveling at an incredible speed of 61 kilometers per second, is displaying a feature that challenges everything we thought we knew about comets. A feature that points directly toward the sun, instead of away from it. This sunward feature has persisted for nearly 6 months across various observation epochs, extending farther than the distance from Earth to the Moon. Meanwhile, 3I, Atlas, continues to exhibit signs of non-gravitational acceleration, an anomaly that cannot be fully explained by its visible outgassing. All of this is occurring as the object shifts in color in ways that mirror what we've seen in comets before, color shifts that often precede the fragmentation of a comet. The conservative explanation here is that 3I, Atlas, represents a new type of comet, one formed under conditions so vastly different from our solar systems that our models simply can't account for its behavior. Perhaps its ice composition is unusual, with exotic volatiles that sublimate in ways we've never encountered before. Or maybe the dust-to-gas ratio is so extreme that large particles dominate the coma, altering the dynamics of radiation pressure in ways we don't yet understand. There's also the possibility that the internal structure of 3I, Atlas, is unlike any comet we've studied. A complex rubble pile held together by forces we cannot yet explain. But there's a less conventional theory, one that has captured the attention of millions who have followed this story from afar. What if 3I, Atlas, isn't entirely natural? What if some component of its behavior suggests design, rather than random cosmic processes? Could the anti-tail, as Avi Loeb provocatively suggested, to be exhaust from a technological propulsion system? It's crucial to be clear here. There is no direct evidence that 3I, Atlas, is artificial. No signals from intelligent sources. No visible structures that could suggest manufactured origins. The object exhibits all the classic features of a comet: gas emissions, dust production, and a measurable coma. The overwhelming consensus among astronomers is that 3I, Atlas, is a natural comet, extraordinary in its behavior, but not supernatural in its origin. However, science advances by taking anomalies seriously and not dismissing them simply because they're uncomfortable, and the anti-tail of 3I, Atlas, is an anomaly that demands an explanation, an anomaly so profound that it could redefine our understanding of comets and interstellar objects. What makes this moment in time particularly significant is that in just 72 hours, we'll have our best opportunity yet to gather detailed data on this enigmatic object. 3I, Atlas, will make its closest approach to Earth on December 19th. Coming within 270 million kilometers, its closest distance in its entire passage through the solar system. At this range, ground-based telescopes with apertures of 30 centimeters or larger should be able to detect the object with the naked eye. Professional observatories will capture spectroscopic data with unprecedented detail. The James Webb Space Telescope, scheduled for observations in December, will focus on the infrared signatures of 3I, Atlas's coma, potentially revealing molecules invisible to optical instruments. If the anti-tail consists of ice fragments, Webb will likely detect the spectral signatures of water and other volatiles in the sunward stream. If it's made of solid particles, Webb's infrared observations will reveal the thermal properties of these objects, and perhaps even their composition. If the non-gravitational acceleration is driven by outgassing, the spectroscopic data should show gas production rates that match the massive mass loss required to generate the observed acceleration. But if none of these predictions hold true, if the data fails to fit within our established models, if the anti-tail remains inexplicable, then we will be forced to reconsider everything we thought we knew about comets. We will be forced to accept that the universe is stranger and more complex than we ever imagined, and this realization could lead to profound discoveries. We will have learned that our sample size of just 2 previous interstellar visitors, Oumuamua and Borisov, was far too small to prepare us for the extraordinary nature of 3I, Atlas. Whether these discoveries are the result of exotic natural processes or deliberate design, we won't know until we look, and the anti-tail of 3I, Atlas, is an invitation to challenge our assumptions, gather new data, and follow the evidence wherever it may lead. In just 3 days, when 3I Atlas makes its closest approach, we'll have the best chance yet to answer these questions. But the anti-tail is far from the only feature of 3I Atlas that demands our attention. As we briefly mentioned earlier, this object shares its designation with another comet that underwent a dramatic transformation, a transformation that has some observers deeply unsettled. The parallels between 3I Atlas and K1 Atlas go far beyond their shared name. Both objects have undergone a similar chromatic transformation. Both are currently transiting through the same celestial region, and one of them has already shattered. When two comets enter the same region of sky, it almost feels like the universe is staging something grand, a cosmic coincidence too perfect to be true. Two objects with the same name, discovered by the same network, both undergoing similar color transformations, both passing through the same constellation, Leo, within weeks of each other. It's almost as if the universe is playing out a scripted drama, too perfect to be believed. If a screenwriter had pitched this scenario for a science fiction film, producers might have rejected it as too coincidental, too neatly structured. But here we are, witnessing it unfold before our eyes. Comet K1 Atlas was discovered in May of this year by the Asteroid Terrestrial Impact Last Alert System, the same network that would detect 3I Atlas just 2 months later. K1 was a solar system comet, born from the Oort Cloud at the farthest reaches of our celestial neighborhood. It was pristine material, never before heated by the sun, carrying the chemical fingerprints of the era when our solar system was still young. K1's trajectory brought it dangerously close to the sun, passing within 50 million kilometers on October 8th. This is 4 times closer than 3I Atlas would get during its perihelion just weeks later. Many astronomers predicted that K1 would not survive the encounter. Its fragile body would be torn apart by the sun's gravity, heat, and radiation. But K1 emerged intact, battered, certainly, but still whole. And when astrophotographer Dan Bartlett captured it on October 29th from June Lake, California, something unexpected happened. K1 was glowing gold. It wasn't the usual green of diatomic carbon, the hallmark of an active comet, nor was it the reflective white glow of a dormant body. K1 was glowing gold, an amber hue that signified profound chemical changes inside the object. Bartlett's observation wasn't the only one. Multiple astronomers across California and Arizona confirmed the same gold color, a golden hue that signaled something unique, something unexpected. David Schleicher, an astronomer at Lowell Observatory, analyzed the spectral data and confirmed that K1 had lost most of its carbon-bearing molecules dicarbon, carbon monoxide, cyanide, all of which contribute to the green glow in comets. Only 2 other comets in history have displayed such extreme carbon depletion. And then, K1 began to fragment. By November 10th, observers noticed the first signs of fragmentation. The comet split into at least 3 distinct pieces by November 11th, with images showing multiple subnuclei and debris scattered throughout space. The golden color had served as a warning, an indication that K1's internal chemistry had reached its limit. As the volatile ices that held the comet together evaporated, the object's structural integrity was compromised, and the nucleus fractured under the immense heat and gravitational stresses. K1 was a solar system comet born from the farthest reaches of our celestial neighborhood, the Oort Cloud, that frozen, icy zone of the solar system's edge. It was embarking on its first journey into the inner solar system, carrying material from an era when our sun was still young. This pristine comet had never before been subjected to the sun's heat, and as it approached our star, it carried the unspoiled chemical signature of the primordial times, offering a glimpse into the raw building blocks of our solar system. However, K1's trajectory took it perilously close to the sun. On October 8th, it passed within a mere 50 million kilometers of our star, 4 times closer than 3I Atlas would come to the sun during its own perihelion just 3 weeks later. The forces at play in such a close encounter are extreme, immense gravitational stresses and searing heat. Many astronomers were convinced that K1 fragile and volatile, would be torn apart by the sun's might. It seemed far too small, far too fragile to survive. Yet, against all odds, K1 emerged intact from its close encounter, battered, certainly, but whole. When astrophotographer Dan Bartlett captured an image of K1 on October 29th from June Lake, California, it revealed something completely unexpected. K1 was glowing not the usual green of a comet, nor the dull white of a dormant body, but a deep, warm amber gold. This golden hue was not a trick of the light. It spoke of fundamental chemical changes happening inside the comet. Bartlett's observation was quickly confirmed by multiple photographers across California and Arizona, all reporting the same astonishing golden glow. This shift to gold was no mere color change, it was a transformation, one that astronomer David Schlicker at Lowell Observatory was quick to investigate. Spectroscopic analysis revealed that K1 had lost nearly all of its carbon-bearing molecules, those crucial compounds like dicarbon, carbon monoxide, and cyanide, which typically give comets their characteristic green glow. The depletion of these substances was so extreme that it placed K1 in a category with only two other comets in recorded history. A profound chemical depletion had set the stage for the comet's eventual demise. As K1 continued its journey, the scientific community was understandably more focused on the upcoming perihelion of 3I, Atlas, an interstellar comet that had captivated astronomers' attention for its otherworldly nature. Cooksey, though fascinating, was quickly overshadowed by its more mysterious cousin. Few noticed as K1 drifted into the constellation Leo the Celestial Lion, a symbol of power and royalty across countless cultures. But this shift was not just a celestial coincidence. Then, on November 10th, the first signs of K1's fragmentation began to appear. By the next day, November 11th, the comet had split into at least 3 distinct pieces, as confirmed by Gianluca Massi of the Virtual Telescope Project. The once coherent body had disintegrated, and scattered debris filled the void where a single nucleus once existed. The fragmentation continued in the days that followed. With each piece fluctuating in brightness and position, the golden glow, it seemed, had served as an early warning, a sign that K1's internal chemistry had reached its limit. The volatile ices, which had held the nucleus together, were depleted, and the once cohesive structure could no longer withstand the immense thermal stress caused by the sun's heat. The golden hue was more than just an optical phenomenon, it had been a signal of imminent destruction. As solar heating continues to stretch the comet's structure, it causes thermal stresses that the weakening nucleus cannot endure. The comet cracks, fractures, and eventually disintegrates entirely. Now, 3I, Atlas, is following an eerily similar path, not in physical space, but in the trajectory of its color changes from red to green, and now to gold. The exact sequence K1 followed before its destruction. As of mid-December, 3I, Atlas, has entered the constellation Leo. It is positioned between Virgo and Leo, slowly drifting toward the heart of the celestial lion. On December 19th, as it makes its closest approach to Earth, it will be located just below Regulus, the brightest star in Leo. By December 27th, it will pass within 8 degrees of Regulus, deep within the same constellation that witnessed K1's golden transformation and ultimate demise. The symbolism of this is not lost on those who follow these events closely. Leo, often associated with the sun and gold in astrological traditions, now hosts 2 comets from the Atlas family, both turning gold. With one already fragmented, the poetic resonance is undeniable, though we must be careful not to let symbolism cloud our scientific analysis. What physical parallels can we draw between these 2 objects, and what do these similarities tell us about the fate of 3I, Atlas, in the days to come? The first striking parallel is the color shift itself. Both comets transitioned from green to gold after perihelion, suggesting similar chemical processes are at play. The primary driver behind this change is the depletion of carbon-bearing molecules once these compounds are no longer sublimating in large quantities. the primary source of color shifts to dust particles, which absorb blue light and reflect red and amber hues, gold, or amber. Hues are often associated with the presence of iron-bearing silicates or complex organic residues in the comet's dust. The second parallel is the timing relative to perihelion. K1 shifted color within days of its closest approach to the Sun, while 3I, Atlas, took approximately 6 weeks post-perihelion to undergo the same transformation. This delay is entirely consistent with the greater distance 3I, Atlas, maintained from the Sun during perihelion K1 came within 50 million kilometers of the solar surface, while 3I, Atlas, only reached 210 million kilometers, roughly 4 times farther. The third parallel is more troubling: the activity level of both comets. K1 displayed heightened activity in the weeks leading up to its fragmentation, with outbursts observed between October 31st and November 4th. Similarly, 3I, Atlas, has been showing signs of increased activity, including its persistent anti-tail and the multiple jets observed in recent images. If these outbursts are indeed precursors to fragmentation, 3I, Atlas, may be nearing a critical point in its journey. But there are reasons for cautious optimism. 3I, Atlas, is almost certainly larger than K1 was, with the Hubble Space Telescope estimating its nucleus diameter to be between 440 meters and 6 kilometers, substantially larger than the typical Oort Cloud comet. Larger nuclei have more thermal inertia, meaning they heat and cool more slowly, which may reduce the thermal stresses that typically lead to fragmentation. Furthermore, 3I, Atlas, has a different origin and presumably a different composition. K1 was a solar system object, formed from the same primordial material as our planets, while 3I, Atlas, is an interstellar object that originated from a star system possibly billions of years older than our own. Its ice chemistry, dust composition, and internal structure could all be fundamentally different, which may affect its ability to survive solar heating. Another key difference lies in their thermal histories. K1 was making its first approach to the Sun, experiencing intense heating for the first time in its existence. 3I, Atlas, according to the leading hypothesis about its origin, was once a short-period comet around its original star, undergoing hundreds or even thousands of close approaches before being ejected into interstellar space. This prior thermal processing may have removed the most volatile and structurally weak components, leaving behind a nucleus that is more resilient to solar heating. The evidence from 3I, Atlas's perihelion passage, supports this theory. Despite passing within 4 astronomical units of the Sun and experiencing heating of approximately 735 watts per square meter, the nucleus appears to have remained intact. Post-perihelion images from Hubble show a single, coherent object, not a fragmented debris field. The anti-tail, regardless of its origin, emerges from a central source, not scattered debris. However, the gold color remains a concern. The shift away from carbon-bearing emissions strongly suggests that the volatile materials that fueled the comet's activity are indeed becoming depleted. If 3I, Atlas, is running low on the ices that have been sustaining its activity, the internal pressures that have maintained its structural cohesion could be shifting in unpredictable ways. The next several days will be critical. The closest approach on December 19th will provide our best observations yet, but it also marks the period of maximum gravitational stress on the comet. While 3I, Atlas, will be 270 million kilometers from Earth, it will be enduring the lingering effects of its solar encounter. The heating from perihelion takes time to penetrate the nucleus, and thermal waves propagate slowly through porous, icy material. The maximum internal temperature might not be reached until weeks, or even months, after the closest approach to the Sun. This means that even though 3I, Atlas, may have survived perihelion intact, a structural crisis could still be unfolding beneath the surface. Cracks could be propagating through the nucleus right now, undetectable to our telescopes, but silently weakening the comet. A fragmentation event could occur at any moment, transforming a single enigmatic interstellar visitor into a chaotic debris field. the pieces of which would scatter through space. What would fragmentation mean for our understanding of 3I, Atlas? In some ways, it would simplify the picture. A cometary nucleus breaking apart under thermal stress is precisely what our models predict. The anomalies, the anti-tail, the non-gravitational acceleration, the unusual spectroscopy could all be explained as the result of a fragmenting comet. A body that has reached the breaking point, its internal structure unraveling as it succumbs to the forces of the Sun. The post-perihelion images from the Hubble Space Telescope have shown a singular, coherent object, a solid form still intact, without the multiple fragmented pieces that would signify disintegration. Yet, despite the apparent stability, the golden hue of 3I Atlas remains unsettling. The shift away from carbon-bearing emissions suggests that the volatile reserves, the very fuels driving its cometary activity, are indeed running dry. This marks a pivotal moment in our understanding of the object. If 3I Atlas is depleting its icy core, it signals a fundamental shift in the internal pressures that once held the object's structure together, and that could very well be changing in ways we can't predict. Over the coming days, our window for observation will be crucial. The closest approach, on December 19th, promises to deliver the most detailed views yet, but it also marks a period of maximum gravitational strain on the comet. As 3I Atlas nears Earth, it will experience the cumulative effects of its solar encounter, an encounter whose thermal impact takes time to fully propagate. The solar heating, which began during perihelion, doesn't immediately reach the deeper layers of the comet's nucleus. Instead, thermal waves gradually work their way through the porous, icy structure of 3I Atlas, and the true internal temperature of the nucleus may not peak until weeks or even months after the closest approach. This means that, even if 3I Atlas appears to have survived perihelion relatively intact, the real structural crisis could be slowly unfolding beneath its surface. Cracks, invisible to our telescopes, may be propagating right now, eroding the comet's structural integrity from within. These fractures could ultimately lead to a sudden and unexpected fragmentation, tearing apart a once enigmatic interstellar visitor and scattering its ancient material into the cosmic void. This imminent possibility looms ever closer, and the next few days will be pivotal. So, what would fragmentation mean for our understanding of 3I Atlas? In some respects, it would simplify the situation, confirming what we already expect from cometary behavior. A cometary nucleus that breaks apart under thermal stress would behave exactly as our models predict. The anomalies, such as the anti-tail, the non-gravitational acceleration, the unusual spectroscopy would all likely fall in line with the consequences of an unstable, fragmenting body. The fragments that would break off would experience varying levels of radiation pressure, which might explain the complex jet structures we've observed. Furthermore, the non-gravitational acceleration we've seen could be a direct result of uneven mass loss as the comet's pieces break apart. But there's also a loss in this outcome. 3I Atlas is only the third interstellar object humanity has ever observed, making it an extraordinary opportunity to study a body that has traveled across the cosmos for billions of years. Oumuamua passed through too quickly for us to study it in detail. Its small size and lack of visible cometary activity made it a mystery that eluded deep examination. Borisov was more cooperative, displaying classic cometary behavior, but it too has now vanished from our solar system forever. 3I Atlas represents our best chance yet to study material from another star system, an opportunity to analyze the composition and history of a body that has formed around a star foreign to our own. If 3I Atlas fragments, it will still offer valuable insight, but it would also mean losing the chance to study it as a complete, intact system. The debris field left behind would be scientifically fascinating, but the opportunity to explore its unified structure, its original form, its history as an integrated object would be gone forever. This is a moment we will not get back. The parallels with K1 Atlas raise another thought-provoking question. Why are both objects exhibiting the same golden color as they move through the same region of the sky? Is it just a coincidence that two separate comets, discovered by the same telescope network, both undergo a similar transformation? Or is there some connection between them that we haven't yet discovered? The rational interpretation might be that it's merely coincidence. Leo is a vast constellation that comets often pass through, and the gold color shift linked to carbon depletion is a well-understood phenomenon in cometary science. The fact that both Atlas comets are displaying this behavior at the same time is striking, but not astronomically extraordinary, considering the broader population of comets. But the human mind has an innate tendency to search for patterns. And sometimes, those patterns are real. Both of these objects share the same origin, both were detected by the same telescope network. Both comets are making their close approach to the inner solar system at nearly the same time. Both transitioned through the same color sequence. And now, one of them has already shattered. Whether these similarities are simply coincidental or reflect a deeper connection, the fact that these two objects are so closely tied in terms of their behavior and their fate is impossible to ignore. This has captured the imagination of people around the world. Discussions about 3I, Atlas, on social media often mention K1's demise as either a forewarning or a precedent for what might soon happen to this interstellar visitor. The astronomical community is watching, documenting every observation, bracing for whatever comes next. Because something big is coming. The December 19th approach will be a key moment. It will provide answers. One way or another, either 3I, Atlas, will demonstrate its resilience, maintaining its integrity as it continues its journey toward Jupiter and beyond, or it will follow K1 into fragmentation, scattering its ancient, interstellar material across the emptiness of space. Before we reach that pivotal moment, however, there is another mystery we need to address, one that has been building since the earliest observations of 3I, Atlas. It involves an element that should not be present in a cometary spectrum without its twin, an element that has puzzled spectroscopists and has led to speculation about the true nature of this interstellar visitor. The nickel enigma, nickel and iron, two elements that are chemically inseparable, often found side by side in the universe, forged in the same stellar furnaces and scattered by the same supernova explosions. When we detect nickel, we expect to find iron, and vice versa. The ratio between these two elements is one of the most consistent chemical signatures in the universe. So, when spectroscopic observations of 3I, Atlas, revealed strong emissions of nickel, but no corresponding signal from iron, astronomers were baffled. It was as if they had found a comet with peanut butter, but no bread. The combination seemed impossible, so contrary to the fundamental principles of chemistry that they initially assumed the data must be wrong. But multiple independent observations confirmed the same anomaly. The Very Large Telescope in Chile first detected the nickel emissions on July 20th. Just 3 weeks after 3I, Atlas's initial discovery, follow-up observations showed that by August 21st, the comet was emitting 6 grams of nickel every second. While 6 grams per second may not seem like a massive amount, over a single day, it adds up to nearly 400 kilograms of nickel vapor. Over a month, that's almost 12 metric tons of nickel. This material is being actively released from the nucleus of 3I, Atlas, vaporizing into the coma and spreading out into the vacuum of space. But through all this, the signature of iron remains completely absent. This raises an even bigger question. How is any nickel or iron ending up in the gaseous coma of 3I? Atlas, nickel, and iron are metals with exceptionally high boiling points far beyond the temperatures the sun can produce at cometary distance. In typical comets, these metals are bound within minerals or metallic grains and are not easily vaporized. So how did 3I, Atlas, manage to release nickel without releasing iron? The answer may lie in a class of compounds known as metal carbonyls. These are volatile molecules where metal atoms, like nickel or iron, are bonded with carbon monoxide groups. When a comet's nucleus warms up, these compounds can sublimate into the coma, carrying their metal atoms with them. Nickel carbonyl NiCO4 is highly volatile and can sublimate at temperatures well below 100 degrees Celsius. iron carbonyl FeCO5 behaves similarly, but it's more reactive than nickel carbonyl and decomposes more easily. So, while solar heating warms the cometary nucleus, these metal carbonyls can sublimate directly into the coma. Once in the coma, the ultraviolet radiation from the sun breaks apart the carbon monoxide groups, releasing free metal atoms, which we can then detect spectroscopically. This process is what we typically observe in solar system comets, where nickel and iron are released in roughly equal amounts. However, 3I Atlas breaks this pattern completely. Nickel is there, but iron is not. This discrepancy is striking. This is no minor imbalance between nickel and iron. It's a complete absence of iron. Despite the presence of nickel, this raises several hypotheses, each with implications for the comet's history and origin. The first hypothesis suggests that iron carbonyls are simply more unstable than nickel carbonyls. They break down more easily when they come into contact with other molecules, such as water. If 3I Atlas contains significant amounts of water ice, this could explain why the iron carbonyls were destroyed before they reached the coma. This would be consistent with the comet's observed water activity after crossing the 2.5 astronomical unit threshold in early September. Another hypothesis focuses on the environment in which 3I Atlas was formed. If it originated in a region with conditions that favored nickel carbonyl formation over iron carbonyls, then the comet could have been enriched in nickel from the beginning. This would provide us with a chemical fingerprint of the star system where 3I Atlas was born, offering new insights into the conditions of its formation. A more speculative hypothesis involves the idea that 3I Atlas's nickel anomaly is not a product of natural chemistry, but of deliberate manipulation by an advanced civilization. Could this unusual nickel emission be the residue of industrial activity? Could an intelligent species have mined cometary material for its nickel, leaving behind the iron? This hypothesis, though fascinating, remains highly speculative. There is no direct evidence for artificial processing, and the nickel anomaly can likely be explained through natural chemical processes. Nonetheless, this idea highlights the breadth of theories that have been sparked by the comet's unusual properties. Whatever the explanation, the nickel enigma remains one of the most compelling and perplexing features of 3I Atlas. It sets this comet apart from the typical solar system objects we've studied, and it adds another layer to the growing list of anomalies that make this object truly unique. As we continue our observations, we may uncover even more surprising insights into the behavior of interstellar objects. The third hypothesis ventures into more speculative territory, particularly intriguing for those who believe 3I Atlas may not be entirely natural. What if the selective enrichment of nickel is not a product of natural chemistry, but rather the result of deliberate processing? Nickel, with its crucial role in industrial applications, from alloys to catalysts to electronic components, could be an element extracted through technology rather than cosmic chemistry. Could an advanced civilization, perhaps far beyond our own, have mined cometary material, selectively harvesting iron for structural purposes while leaving behind nickel compounds? Under this speculative scenario, the observed nickel emission from 3I Atlas could be nothing more than residue from industrial activity, the result of an alien civilization's mining efforts. But let's be clear, this hypothesis is highly speculative. There is no direct evidence to support the notion that 3I Atlas has been artificially processed. The anomaly in nickel can still be explained through natural chemical processes without resorting to the notion of technological intervention. Yet, this hypothesis highlights just how extraordinary this object is. It stirs the imagination, compelling scientists to consider the possibility that we are witnessing something far beyond the ordinary processes of our understanding. From conventional theories to more far-flung speculations, the behavior of 3I Atlas has generated a range of theories and ideas, some grounded in known science, others veering into the extraordinary. Regardless of the explanation, the nickel anomaly is just one example of the ways in which 3I Atlas distinguishes itself from typical solar system comets. But it's not only the nickel-to-iron ratio that stands out. The overall abundance of nickel in the coma has increased far more rapidly than expected as 3I Atlas approaches the Sun. Standard models of cometary activity predict gradual increases in gas production as solar heating intensifies. But 3I, Atlas, is defying these expectations with an accelerated rise in nickel emissions. This sharp uptick suggests an extraordinary sensitivity to temperature, or perhaps an entirely unconventional internal structure. The discovery of cyanide adds yet another layer to this growing chemical puzzle. Cyanide HCN is a common byproduct in comets. Formed when solar radiation breaks apart complex carbon, hydrogen, nitrogen compounds. The mere presence of cyanide in 3I, Atlas, is not shocking. Yet its close relationship with nickel production is, both elements saw their emissions increase simultaneously as the comet neared the Sun, indicating they might stem from the same source material or be linked by the same sublimation processes. One particularly intriguing possibility is that the nickel and cyanide are both released from the same organic matrix. Organic compounds, which give comets their reddish hue, often incorporate metal atoms within their molecular structures. As these organics sublimate and decompose, they could simultaneously release both metal atoms and simpler molecules like cyanide. This could explain the correlated production rates of nickel and cyanide and potentially the unusual nickel-to-iron ratio. If the organic material that coats 3I, Atlas, preferentially incorporates nickel over iron, then the transition in its color could be tied to the sublimation and decomposition of these organics. Initially, 3I, Atlas, displayed a deep red hue, likely due to organic compounds it had gathered during its interstellar journey. As it passed closer to the Sun, these organics began to break down, releasing nickel, cyanide, and eventually the diatomic carbon that caused the previous green glow. Now, with the organics mostly depleted, the object has shifted to a golden coloration, and the gas production has significantly slowed. This scenario offers an internally consistent narrative that aligns well with known cometary chemistry. Yet, this raises even more questions. Where did the organics originate? How did they accumulate on 3I, Atlas, during its long voyage through the stars? And why is the nickel-to-iron ratio so strikingly different from what we see in solar system objects? The answer to these questions may lie in the interstellar medium itself. Space between stars is not empty. It is filled with a faint, diffuse soup of atoms, molecules, and tiny dust grains, the remnants of ancient stars and supernovae. 3I, Atlas, traveling at 61 kilometers per second through this vast expanse, would have continuously swept up these materials over billions of years, accumulating a coating of interstellar frost. The composition of this interstellar frost would vary depending on the regions it traversed in the galaxy. In areas of recent star formation, the interstellar medium could be enriched with elements produced by massive stars. In the remnants of supernovae, the frost would reflect the specific nuclear reactions that took place in those stellar explosions. The unique nickel signature found in 3I, Atlas, could, in fact, to be a direct measurement of the interstellar material it has been traveling through a chemical fingerprint of its journey across the galaxy. This interpretation transforms 3I, Atlas, from an oddball comet into a cosmic messenger, carrying information about the chemistry of interstellar space that we could never have gleaned in any other way. Every gram of nickel in its coma, every molecule of cyanide, every grain of reddish organic dust represents material that 3I, Atlas, has gathered over its long and lonely journey between the stars. By studying this material, we are studying the very galaxy that gave birth to this object. The upcoming observations from the James Webb Space Telescope are crucial in unlocking the mystery of this nickel enigma and unveiling the broader chemical story that 3I, Atlas, carries with it. Webb's infrared spectrometers will be able to detect molecular signatures that remain invisible to optical telescopes, possibly revealing compounds present in the coma that have yet to be identified. If there are iron-bearing compounds hiding in the comet, ones that don't produce visible emission lines, Webb might be able to detect them. Webb can also probe the thermal properties of the dust in the coma, determining if the grains are made of silicates, carbonaceous materials, or something else entirely. This will help us better understand the conditions under which 3I, Atlas, formed and evolved. potentially shedding light on why its chemical composition differs so dramatically from that of typical solar system comets. The nickel anomaly also has profound implications for the question of whether 3I Atlas will fragment. Metal carbonyls are volatile compounds that contribute to a comet's overall ice budget. If 3I Atlas has unusual abundances of these compounds, they might be depleting faster than expected, and this could impact the structural integrity of the comet's nucleus. The nickel emission we observe might signal that binding materials within the nucleus are being lost, gradually weakening the object from the inside. Alternatively, this unusual chemistry might be enhancing 3I Atlas's structural stability. If 3I Atlas has different ice compositions than solar system comets' compositions with different melting points or thermal expansion coefficients, it could be responding to solar heating in ways that our current models simply cannot predict. The same chemical differences that produce the nickel anomaly might also contribute to 3I Atlas's unexpected resilience. We are still grappling with how these interstellar objects work, and 3I Atlas is forcing us to confront the limits of our knowledge. What we've learned so far suggests that every assumption we've made about comets, based on solar system experience, must be re-examined in the light of this alien visitor's behavior. And the nickel anomaly is one of the clearest reminders that our assumptions may be wrong. But this is only one of many anomalies. The list is growing as we accumulate data from months of observation. Each anomaly is a puzzle that challenges our current understanding of cometary science. There are now 13 distinct anomalies on the list. Each one presents a unique challenge, pushing the boundaries of what we know about celestial bodies, like 3I Atlas. Some of these anomalies may ultimately prove to be artifacts of our observation methods or results of our incomplete understanding, but others could point to genuinely new phenomena that could change our conception of interstellar objects forever. One researcher has even argued that the accumulation of these anomalies is so extraordinary that the probability of them all occurring naturally is so low that we must entertain alternative explanations. While this theory remains controversial, it underscores just how extraordinary 3I Atlas truly is. These anomalies are real, and they have been documented in peer-reviewed observations by multiple independent teams. These 13 anomalies are not outliers or failures of observation, they are invitations to learn. They challenge our models, defy our expectations, and refuse to conform to the established theory of cometary behavior. Anomalies are not roadblocks, they are the stepping stones to new discoveries. 3I Atlas has presented us with more of these stepping stones than any object in recent astronomical history. Each one of these 13 anomalies represents a distinctive feature of 3I Atlas that defies conventional cometary science. Taken individually, any one of them could be dismissed as a statistical anomaly or a measurement error, but taken together, they paint a picture of an object that is genuinely unprecedented, an object that is forcing us to expand the boundaries of our understanding. Let's take a closer look at each of these anomalies. The first, and perhaps most striking, is the trajectory of 3I Atlas, which is aligned within just 5 degrees of the ecliptic plane. This is a remarkably rare alignment, with a probability of just 0. R. Most interstellar objects arrive from random angles, but 3I Atlas entered our solar system almost precisely along the same plane that our planets orbit. This alignment maximizes the number of close planetary encounters during its passage through the solar system, increasing the potential for scientific observations. Moreover, it has minimized the rocket fuel required for any future space mission, trying to match velocities with our planets. This alignment is so precise that it feels as if it was almost designed for a scientific mission to study the object. The second anomaly is the persistent sunward jet, or antitail, that has been observed since 3I Atlas's first appearance in July. This feature, which extends over 500,000 kilometers toward the Sun, defies our understanding of radiation pressure and continues to evade explanation by any conventional cometary model. This peculiar feature has been visible ever since the initial Hubble observations in July, growing steadily to extend more than 500,000 kilometers toward the Sun. It defies the fundamental physics of radiation pressure, a characteristic that no conventional model has been able to explain convincingly. Anomaly 3 The nucleus of 3I, Atlas, appears to be roughly 1 million times more massive than the interstellar visitor Oumuamua and 1,000 times more massive than Borisov. This startling mass discrepancy is further compounded by its velocity, which surpasses that of both previous interstellar visitors, making its combination of mass and speed statistically improbable. The odds of this anomaly occurring are less than 0.1%, when compared to the population of predicted interstellar objects. Anomaly 4 revolves around the remarkable precision of 3I, Atlas's arrival timing. It was fine-tuned in such a way that it passed within mere tens of millions of kilometers of Mars, Venus, and Jupiter, while somehow remaining completely unobservable from Earth at perihelion. The probability of such a finely orchestrated sequence of planetary encounters and Earth geometry has been estimated at a mere 0.5. It's as though the object was purposefully threading a needle through our solar system, maximizing scientific opportunities for observing other planets, while expertly avoiding detection during its closest approach to the Sun. Anomaly 5 brings us to an even more striking coincidence. The trajectory of 3I, Atlas, intersects with the exact direction of the famous WOW signal detected by the Big Ear radio telescope in Ohio back in 1977. The WOW signal, a 72-second burst of apparent artificial radio emission, has never been observed again. The coincidence between the direction of the WOW signal and 3I, Atlas's arrival vector, carries a probability of approximately 0.5, assuming both are random events. This connection has intrigued astronomers and set imaginations alight. Anomaly 6 highlights the color evolution of 3I, Atlas, from red to green, and now to gold, a sequence that has strangely mirrored the transformation of the K1 Atlas comet, which ultimately fragmented. Although color shifts in comets are well documented, the specific timing and sequence of these changes in 3I, Atlas, are far from ordinary. Anomaly 7 concerns the detection of nickel emissions without the corresponding presence of iron, a chemical signature that has not been observed in any known solar system, comet, and defies the expected behavior of metal carbonyl sublimation. Anomaly 8 involves non-gravitational acceleration, as detected by JPL's Horizon tracking system, which follows an inverse square law in relation to the Sun's distance. This unique acceleration pattern could either be the result of massive outgassing or, as some have suggested, the workings of an advanced technological propulsion system. Anomaly 9 showcases the bizarre behavior of 3I, Atlas's jets, which remain consistently oriented over millions of kilometers. Despite a measured rotation period of approximately 16 hours, conventional models predict that such jets should spiral, but 3I, Atlas, defies this expectation with perfectly collimated jet structures. Anomaly 10 raises concerns about the object's extraordinary brightness increase near perihelion. The comet's brightness increased by several orders of magnitude, far exceeding typical cometary behavior at similar heliocentric distances. This suggests either unusual outgassing activity or an anomaly in the comet's surface properties. Anomaly 11 centers around the question of the surface area required to absorb enough sunlight to power the observed mass loss. The surface area calculations suggest a need for an absorbing area far greater than the nucleus size constrained by Hubble observations, an impossible scenario according to current comet models. Anomaly 12 returns to the persistent anti-tail that defies conventional physics. Despite the rotation of the nucleus, this sunward extension maintains a coherent structure that should have been dissipated by radiation pressure and rotational forces. Anomaly 13 involves rapid brightening and behavior near perihelion, which suggests the massive evaporation of at least 13% of the comet's total mass, or possibly some other mechanism entirely. If this mass loss was genuine, it would have caused significant structural stress on the object yet. Preliminary post-perihelion observations show the object intact. These accumulated anomalies cannot simply be dismissed as minor quirks in data or errors of measurement. The conservative interpretation here is that 3I, Atlas, represents a new class of interstellar comet, one formed under conditions that differ drastically from anything we've seen in our solar system. Its composition and structure appear to lie beyond the realm of our current models, forcing us to reconsider the very nature of these cosmic wanderers. However, it is not about dismissing these anomalies. It's about acknowledging that our current sample size of interstellar objects is too small to know what normal looks like. We've observed only 3 such interstellar objects. So drawing conclusions about typical behavior based on such a limited sample is statistically meaningless. The fact that 3I, Atlas, is unlike anything we've encountered before doesn't mean it is unnatural. It simply means the universe is much more diverse than we had assumed. This interpretation, which holds that these anomalies are part of the natural variation of interstellar objects, is favored by the majority of astronomers working on 3I, Atlas. The alternative interpretation, most prominently supported by Avi Low and a minority of researchers, argues that the accumulation of anomalies exceeds what can be comfortably attributed to natural variation. They suggest that the coincidences, the probabilities, and the coordination of features are simply too unlikely to be explained by random processes. There's something about 3I, Atlas, that seems to demand an explanation beyond exotic natural chemistry. Low, in his more recent writings, has been careful to maintain epistemic humility, estimating a 30–40% likelihood that 3I, Atlas, is not entirely of natural origin. While the most likely conclusion still points to a natural comet, the sheer volume of unexplained features warrants serious consideration of alternatives. The hypothesis Low has proposed suggests 3I, Atlas could be a probe sent by an extraterrestrial civilization, targeting our solar system for reconnaissance or other purposes. According to this hypothesis, the comet's activity could be a disguise, with the accumulated interstellar material acting as a cover for an artificial core. The anti-tail could potentially be thrust exhaust, the trajectory alignment, deliberate navigation, and the timing of the passage carefully orchestrated to maximize data collection from our planets while minimizing detection by Earth-based observatories. This theory makes several specific predictions. If 3I, Atlas, is artificial, it should not fragment under thermal stress. As technological artifacts are built to endure, non-gravitational acceleration would persist even as outgassing declines, much like thrusters operating independently of volatile reserves. If this hypothesis holds any weight, close observations during the December 19th closest approach will provide crucial data. High-resolution imaging should reveal more about the shape and surface features of the nucleus. Spectroscopic observations will characterize the outgassing, while radio telescopes may be able to detect any unusual emissions that would point to technological activity. If 3I, Atlas, behaves exactly like a natural comet, this hypothesis will lose support. But if it continues to defy our expectations, the case for a technological origin will grow stronger. However, we must approach the evidence with caution. The human mind is naturally inclined to perceive patterns even where none exist, to attribute meaning to coincidence, and to favor more sensational explanations. History has shown us that many phenomena that initially seemed anomalous were later explained by conventional physics, such as the canals on Mars, the pulsating radio signals once thought to be alien beacons, or the anomalous acceleration of the Pioneer spacecraft. In each of these cases, premature speculation about exotic explanations turned out to be unfounded. The lesson here is not that anomalies should be ignored, but that they should be studied with care, patience, and an open mind, with conclusions proportional to the evidence at hand. 3I, Atlas, has been under observation for less than 6 months, and although we have data from a range of telescopes, we are still at the beginning stages of understanding this object. The anomalies are real, but their interpretation remains uncertain. The responsible approach is to continue gathering data, to test hypotheses against new observations, and to let the evidence guide us toward conclusions rather than letting preconceived notions shape our understanding. What we can state with confidence is that 3I, Atlas, is extraordinary, regardless of its origin. Whether it is a natural comet or something else entirely, it is showing us that interstellar objects can be far more complex than anything we've observed within our solar system. If it is something more than a comet, it's teaching us that the universe is full of possibilities we have yet to comprehend. The exploration of 3I Atlas continues to be a remarkable journey, with each anomaly revealing new complexities. As observations unfold, the 13 anomalies we've uncovered so far will either multiply or be resolved, each discovery deepening our understanding of this extraordinary interstellar visitor. With the approaching December 19th closest approach, we are poised to receive a wealth of data that will surpass anything we've been able to observe at greater distances. But these observations are not confined to Earth-based telescopes alone. A network of spacecraft scattered across the solar system has been meticulously tracking 3I Atlas, gathering vital data from perspectives that ground-based instruments simply cannot provide. X-ray satellites have detected emissions from the coma. Infrared instruments have picked up crucial thermal signatures, and spacecraft positioned at Mars captured stunning images during the October close approach. This multi-wavelength, multi-platform campaign is unlike anything we've seen before in the study of interstellar objects, providing an unprecedented opportunity to analyze an alien body in intricate detail. The results of this campaign are still in the process of being analyzed, with some findings already published while others remain under peer review. But together, these observations are piecing together the most comprehensive portrait of a visitor from beyond our solar system ever assembled. And in the next chapter, we'll dive into the intriguing details of the X-ray observations. When space agencies directed their most sensitive high-energy instruments towards 3I Atlas, they uncovered something remarkable, an X-ray glow extending hundreds of thousands of kilometers from the nucleus, revealing processes invisible to optical telescopes. The discovery of X-rays is a striking addition to the growing body of evidence surrounding this mysterious object. There's a poetic irony in using X-rays to study a visitor from another star system. X-rays were first discovered by Wilhelm Röntgen in 1895 during his experiments with cathode ray tubes. The X in X-ray stood for the unknown, an enigmatic force that was beyond comprehension. And now, 130 years later, we're using these very X-rays to study an object whose nature remains equally uncertain, hoping that these high-energy photons will reveal secrets that visible light cannot reach. The first X-ray detection of 3I Atlas came from the Japanese Space Agency's X-RISM mission, which launched in September 2023. From November 26th to 28th, X-RISM conducted a Target of Opportunity campaign, collecting 17 hours of valuable data. However, due to the limitations of the satellite's viewing angle, X-RISM could only observe 3I Atlas when it was more than 60 degrees away from the Sun, restricting the available observation window. The images captured by X-RISM revealed an astonishing X-ray glow extending approximately 5 arc-minutes from the comet, which corresponds to a physical scale of about 400,000 kilometers at the comet's current distance. What's extraordinary about this glow is that it's not concentrated at the nucleus. Instead, it diffuses throughout the surrounding space, tracing the outer reaches of the comet's coma. Shortly after X-RISM's observations, the European Space Agency's XMM Newton joined the effort. On December Dryad, XMM Newton focused its European photon imaging camera on 3I Atlas for around 20 hours. When the comet was about 284 million kilometers from Earth, XMM Newton's EPIC PN camera, one of the most sensitive X-ray detectors ever created, was able to register individual X-ray photons and measure their energies with incredible precision. Both spacecraft detected the same phenomenon. 3I Atlas is emitting X-rays. More precisely, the gas surrounding the comet is producing X-rays through its interaction with the solar wind. To understand why this matters, let's take a step back and explore how comets typically produce X-rays. It was a surprise when the first cometary X-ray emission was detected by the Rosat satellite in 1996, during observations of comet Hyakutake. Comets, being cold objects with temperatures just a few hundred degrees at most, are far too cool to produce thermal X-rays on their own. So, where do the X-rays come from? The answer lies in a process called charge exchange. The solar wind, a constant stream of charged particles from the Sun, contains proton, electrons, and heavier ions like carbon, nitrogen, and oxygen in various states of ionization. These ions have been stripped of electrons by the extreme temperatures in the Sun's corona, making them eager to capture electrons from other sources. When these ions encounter the gas clouds surrounding a comet, they find a source of electrons in the neutral atoms and molecules within the coma. This interaction causes the ions to capture electrons, which results in the emission of photons as the electrons drop to lower energy states. For highly charged ions, these emissions often fall within the X-ray range. This is why we see the diffuse glow of X-rays surrounding any active comet. The X-ray emission from 3I, Atlas, is not surprising, given that any active comet releasing gas into the solar wind will produce these charge exchange X-rays. What makes these particular observations significant is that they provide insight into gases that would otherwise be incredibly difficult to detect. Optical and ultraviolet spectroscopy is great for detecting certain molecules, but there are fundamental molecules like molecular hydrogen H2 and nitrogen N2 that remain nearly invisible to these methods. X-ray observations can reveal these elusive molecules, especially when solar wind ions interact with hydrogen or nitrogen molecules. These interactions produce distinctive X-ray signatures, allowing us to study these molecules in detail. This is especially significant because one of the leading hypotheses about Oumuamua's anomalous acceleration suggested that it might be composed of exotic ices, possibly pure hydrogen or nitrogen ice, which would sublimate without leaving visible gas signatures. If 3I, Atlas, shows evidence of hydrogen or nitrogen in its X-ray spectrum, it would lend weight to the hypothesis that interstellar objects may harbor ice compositions fundamentally different from those of solar system comets. On the other hand, if the X-ray data reveals only the usual water and carbon dioxide emissions, it would reinforce the idea that 3I, Atlas, is chemically similar to known comets. Despite its interstellar origins, preliminary analysis of the X-RISM data, released on December 6th, shows X-ray excesses at energies corresponding to carbon, nitrogen, and oxygen ions, signatures expected from charge exchange with a typical cometary coma. The X-ray glow is diffuse and extends in patterns that align with the known structure of the gas cloud surrounding 3I, Atlas. While nothing in the initial data screams artificial or anomalous, there are subtleties that require further scrutiny. The relative intensities of different X-ray lines could reveal variations in the composition of the target gas, suggesting unusual molecular abundances. Small variations from the expected patterns could hint at something remarkable. Additionally, the spatial distribution of the X-ray emissions could reveal asymmetries or structures not visible in other wavelengths. Variability in the emissions, particularly when solar wind conditions change, could suggest discrete events at the nucleus, such as outbursts or structural shifts. Observations during the X-RISM window coincided with heightened solar activity, which should have amplified the X-ray emission, potentially making faint features detectable. This alignment of solar activity and the comet's position has sparked interest, as it almost feels like the Sun itself is illuminating 3I, Atlas, for our benefit. However, we must be cautious about jumping to conclusions. The Sun often has active regions, and any comet moving through the inner solar system will experience similar alignments. Nevertheless, what does this X-ray emission tell us about the physical state of 3I, Atlas? The extent of the X-ray glow, reaching hundreds of thousands of kilometers from the nucleus, indicates substantial gas production. Material must be continuously flowing outward to maintain such a large coma, which is consistent with the comet actively outgassing. However, this does not completely match some of the surprisingly limited visible gas signatures reported by some observers. This discrepancy could be due to the comet releasing gases that don't produce strong optical emissions, such as H2, N2, or noble gases like argon or neon. Alternatively, it might reflect difficulties in measuring outgassing rates, as these depend on assumptions about gas temperatures and excitation conditions that might not apply to an interstellar object. The December 3rd XMM Newton observations provide additional temporal information, allowing astronomers to compare how the X-ray emission evolves as the comet moves through the solar system. If sudden changes are detected, It could indicate discrete events at the nucleus, perhaps outbursts or shifts in structure. Steady changes would suggest a more quiescent, normal state of cometary activity. The X-ray observations also offer a rare opportunity to search for features that could suggest non-natural origins. Technological artifacts might produce X-ray signatures distinct from charge exchange, such as emissions from electronic systems, nuclear power sources, or unknown processes. So far, no such anomalies have been detected, but the data is still being analyzed carefully. As always, the scientific process remains rigorous, and any claims of unusual emissions would require extraordinary evidence and invite careful scrutiny. X-ray astronomy is a complex field that demands precise data reduction, and any premature speculation is avoided. What we can definitively say is that 3I Atlas is cooperating with our observational efforts, unlike Oumuamua, which was small and inactive. 3I Atlas is large and active enough to produce detectable signals across multiple wavelengths. This opportunity has not been squandered. Ground-based telescopes from all over the world, along with space-based assets from NASA, ESA, and JAXA, have contributed their findings. Amateur astronomers have also added valuable data, complementing the professional campaigns. Together, they've created an unprecedented dataset for an interstellar object. The X-ray observations are just one part of this massive scientific endeavor. Optical telescopes have tracked the color evolution, infrared instruments have examined thermal properties, and radio telescopes have sought out unusual emissions. Radar facilities have even tried to bounce signals off the nucleus to better understand its size and surface properties. Every method reveals a new facet of 3I Atlas. Each observation adds another piece to the puzzle, and the picture that is emerging is one of an incredibly complex object, with multiple active processes occurring simultaneously. The X-ray glow traces the outermost reaches of the coma, where cometary gas meets solar wind. Optical emission shows the dust and smaller molecules closer to the nucleus, while infrared signatures reveal the thermal state and volatile content. The upcoming December 19th closest approach will provide the most detailed data yet. X-ray observations will allow scientists to explore deeper into the faint emission regions. Optical telescopes will refine their resolution, capturing finer details in the coma's structure. Spectroscopic campaigns will achieve better signal-to-noise ratios, potentially revealing trace species that have remained hidden at greater distances. As 3 Atlas continues its journey through the cosmos, it will soon begin its long trek away from the Sun, first heading toward a potential encounter with Jupiter before venturing into the dark void of interstellar space. The X-ray emission will gradually fade as the object moves farther from the Sun, resulting in less gas being produced. Likewise, the optical signatures, which have been an intriguing feature of this cosmic wanderer, will slowly dim as the reflected sunlight weakens, diminishing the visibility of the comet's spectacular coma. Eventually, even the most powerful telescopes will lose track of this enigmatic interstellar messenger, and it will fade back into the cosmic backdrop from which it emerged, its brief but captivating passage through our solar system becoming just another lost memory in the vastness of the universe. Yet, before that inevitable moment, there is still a critical question that must be addressed. The recent X-ray observations have provided evidence that 3 Atlas is releasing gas at substantial rates. The antitail suggests that material is being ejected in a remarkably irregular pattern, and the non-gravitational acceleration implies that forces beyond gravity are influencing the object's movement. All of these unusual phenomena are placing immense stress on the comet's nucleus. The question remains, will this stress be sustainable? Can 3 Atlas endure the accumulated effects of its close solar passage? Or will the golden hue and chemical depletion be harbingers of its inevitable destruction? The fragmentation clock is ticking. And as we near the pivotal December 19th observation window, the astronomical community is eagerly awaiting to see whether this interstellar visitor will remain intact or follow in the footsteps of its namesake, Kine's Atlas. By breaking apart under the immense pressure of solar heat, every comet that approaches the Sun faces an existential test. But for some, this test proves fatal. The very warmth that awakens their dormant ices also threatens to tear them apart. As volatile materials sublime from the comet's surface, they carry away dust and create the magnificent tails that have inspired awe for millennia. However, this sublimation comes at a significant cost. Material is lost, mass decreases, and internal stresses begin to build as different regions of the comet heat at different rates. For some comets, this uneven heating leads to destruction. 3E Atlas has already passed one critical milestone. Its October 29th perihelion brought it to within 4 astronomical units of the Sun, subjecting it to heating of over 700 watts per square meter. It emerged from this encounter seemingly intact, resuming its journey through the inner solar system without immediate signs of fragmentation. Yet, the test is far from over. Thermal waves propagate slowly through a comet's porous, icy material. While the surface responds quickly to changes in solar illumination, heating during the day and cooling at night, the interior takes much longer to adjust. Heat conducts inward over a period of weeks to months, gradually raising temperatures in the deep, volatile rich regions of the nucleus. For an object like 3 Atlas, which may be several kilometers in diameter, this delayed response could mean that the maximum internal stress from its perihelion encounter may not occur immediately, but could develop gradually over the coming weeks or even months. This explains why some comets appear to fragment well after their closest approach to the Sun, leaving observers surprised by the delay. K1 Atlas vividly demonstrated this pattern. While it survived its perihelion on October 8th, passing within 50 million kilometers of the Sun without immediate incident, the damage had already been done. It appeared to have escaped destruction. But by early November, outbursts began signaling internal disturbances. And by November 11th, fragmentation was confirmed. The comet that had defied predictions of its demise eventually succumbed to the forces set in motion during its solar encounter. 3 Atlas's situation is different. Its perihelion was less extreme at 4 astronomical units compared to K1's closer 33 astronomical units, and the heating it experienced was milder. This means that the thermal penetration into the comet's nucleus will proceed more slowly, and structural stresses will accumulate gradually. If fragmentation is going to occur, it may not happen immediately. The gold color shift that we've observed, however, suggests that chemical processes similar to those in K1 are already underway. The depletion of carbon-bearing molecules, the transition from gas-dominated to dust-dominated emissions, and the exhaustion of volatile reservoirs are all warning signs that have typically preceded fragmentation in other comets. If fragmentation does occur, it will likely begin with small structural failures, cracks forming along zones of weakness in the nucleus. These cracks can be initiated by thermal stress, rotational forces, or the pressure exerted by escaping gases. Once a crack widens enough, it can penetrate deeper into volatile-rich regions, triggering sudden bursts of gas that further destabilize the structure. Fragmentation is rarely instantaneous. It tends to occur gradually, with pieces breaking off one at a time. Like icebergs carving from a glacier, the main body continues its trajectory, while the fragments slowly drift away, eventually becoming distinct objects in their own right. K1 Atlas followed this very pattern, splitting into at least 3 major fragments over several days, with each fragment evolving independently. For 3 Atlas, fragmentation would likely begin to show itself as asymmetries in the coma, rather than a smooth, centrally condensed structure. We might see elongation or multiple condensation points, indicating multiple sources of activity. High-resolution imaging may reveal separate fragments if they drift far enough apart, and variations in brightness could suggest the exposure of fresh material or the complete disintegration of smaller pieces. Some amateur astronomers, such as Drew Doss, have reported what they describe as a color shift in recent images of 3A Atlas, noting a transition from green to gold in independent captures from around the world. Doss has explicitly linked this to K1's color shift before fragmentation, warning that 3 Atlas might be on the verge of falling apart. Professional astronomers, however, have remained cautious. and the official assessment based on Hubble imagery and ground-based observations through mid-December is that 3 Atlas remains a single, coherent object. While the coma structure is unusual, with its persistent anti-tail and complex jet features, there is currently no clear evidence of nuclear fragmentation. The brightness variations are consistent with changes in activity levels rather than structural failure. But the situation is still evolving. Observations from the December 19th closest approach will be critical in providing answers. At the closest distance, ground-based telescopes will achieve their highest angular resolution on 3A Atlas. Any fragments separated by even a few hundred kilometers should be resolvable. Any gross asymmetries in the nucleus should be visible. The stakes are not only scientifically significant, but also profound for the opportunity to study an interstellar object. If 3 Atlas fragments, we lose the chance to study it as a coherent whole, its structure and history as a single entity. The debris cloud that would result would still be valuable, potentially exposing interior material that would otherwise remain hidden. But the opportunity to observe its integrated system will be lost. Interstellar objects are rare, and while our detection capabilities are improving, we still expect to find only a handful of such objects per decade with current technology. The Vera Rubin Observatory, now online, will greatly increase our discovery rate. But 3 Atlas may remain the largest and most active interstellar visitor for years to come. Losing it to fragmentation before we have fully understood it would be a scientific tragedy. There are reasons for optimism. However, leading hypotheses suggest that 3 Atlas was once a short-period comet in its original solar system, undergoing hundreds or even thousands of close approaches to its host star before being ejected into interstellar space. This prior thermal processing would have removed many of the most volatile and structurally weak components, leaving behind a nucleus that has already been tested and tempered by these past solar encounters. Such an object may be more resilient than a pristine object like K1, which was making its first approach to a star. The evidence from the James Webb Space Telescope also supports this interpretation, showing that the surface of 3 Atlas has been exposed to cosmic rays for billions of years, with radiation damage extending up to 20 meters deep. This outer layer may act as an insulating crust, protecting the interior from rapid temperature fluctuations and reducing thermal stresses. Additionally, the size of 3 Atlas, potentially several kilometers across, works in its favor. Larger nuclei have more thermal inertia, meaning they heat and cool more slowly, which helps reduce the risk of catastrophic failure. However, we cannot be certain until we observe. The gold color shift remains concerning, and the elevated activity level suggested by the anti-tail and jets indicates ongoing processes that could destabilize the nucleus. The non-gravitational acceleration suggests forces acting on the object, which may trigger structural failure, particularly through asymmetric mass loss. As we approach the December 19th observation window, we are on the edge of a momentous event that could alter everything. The December 19th closest approach coincides with a new moon, which provides the darkest skies for astronomers, ensuring the clearest observations. Both amateur and professional astronomers will have optimal conditions for observing 3 Atlas. Ground-based telescopes will achieve their highest angular resolution, and space-based assets like the Hubble and James Webb Space Telescopes will provide complementary data. These observations will be crucial in resolving the structural integrity of the nucleus. High-resolution imaging will determine whether 3 Atlas remains a single object or has started to fragment. The anti-tail and jets will be scrutinized for clues, and spectroscopic observations will allow astronomers to measure gas emissions with unmatched precision. This data will reveal whether the comet's trajectory deviates from pure gravitational motion, indicating evolving outgassing patterns or other processes affecting its movement. The December 19th observations are more than just a scientific opportunity. They are a chance to capture something truly unique. For anyone with suitable equipment, this is the moment to observe, document, and contribute to this historic event. Even the most modest equipment can contribute valuable data to the growing understanding of this extraordinary interstellar visitor. This unusual resilience in 3 Atlas might stem from its unique history. Unlike pristine comets, like K1 Atlas, which are encountering a star for the first time. 3E Atlas likely carries with it a long history of travel through the vast reaches of interstellar space. Over the course of its cosmic journey, its surface has likely been desiccated to a significant depth, causing the most volatile components to have long since been exhausted. What remains may well be a relatively stable core, hardened by eons of exposure to the void, better equipped to withstand the mild heating it now faces as it makes its way through our solar system. The data from the James Webb Space Telescope strongly supports this interpretation. It has revealed that the surface of 3A Atlas bears the unmistakable marks of cosmic ray exposure extending up to 20 meters deep, a testament to its long and arduous passage through the cold, empty expanse between stars. This outer layer, damaged by the harsh environment of deep space, may act as an insulating crust, effectively shielding the interior from rapid fluctuations in temperature and significantly reducing the thermal stresses that often plague comets that are experiencing their first intense solar encounter. In addition, the size of 3 Atlas works to its advantage. Larger cometary nuclei, such as 3 Atlas, have greater thermal inertia, meaning they respond more slowly to changes in temperature. Unlike a small comet with a 500-meter nucleus, which might rapidly heat up and cool down under the influence of the sun, the interior of a larger, 5-kilometer body like 3 Atlas responds much more gradually. The temperature gradients within it are smaller, the thermal stresses are less intense, and thus the likelihood of catastrophic structural failure is considerably reduced. However, despite this apparent advantage, we cannot be certain until we have more data. The continuing shift to a golden hue remains a cause for concern. As it suggests that the chemical processes inside the comet are still evolving, the elevated activity levels indicated by the persistent antitail and the dramatic jets suggest that ongoing internal processes could still destabilize the nucleus. Furthermore, the non-gravitational acceleration seen in the comet's trajectory implies that external forces, likely driven by asymmetric mass loss, are influencing its movement, potentially triggering structural failure. The upcoming December 19th observation window holds tremendous significance. It coincides with a new moon, providing the darkest skies possible for ground-based observers to capture the most detailed images yet. The timing is perfect for maximizing the scientific return from this closest approach, offering amateur astronomers with appropriately sized telescopes, at least 30 centimeters or larger, the chance to observe this rare cosmic visitor under ideal conditions. Meanwhile, professional observatories around the world have prepared for this critical observation campaign. The Hubble Space Telescope will capture high-resolution imagery, enabling it to resolve structures down to just a few thousand kilometers. The James Webb Space Telescope, with its unrivaled infrared capabilities, will examine the comet's thermal signatures in unprecedented detail. Ground-based spectroscopy will provide the finest data yet on the gas emissions coming from the coma, with sensitivity far beyond what has been possible at greater distances. If 3 Atlas fragments, these observations will document the event in real time. If it remains intact, they will provide the most detailed portrait of an interstellar object we've ever seen. Either outcome will significantly advance our understanding of these mysterious visitors. However, most astronomers hope for the survival of the comet, not because fragmentation wouldn't be scientifically valuable, but because intact survival means we will have more opportunities to study this remarkable object as it continues its journey through the solar system. Every additional month of observation adds valuable insights. The more we learn, the better we can refine our models and test our hypotheses about the behavior of interstellar objects. The longer 3 Atlas remains intact, the more we will understand about its composition and structure. However, the fragmentation clock is ticking, driven by thermal processes that we can model, but cannot directly observe. The heat deposited at perihelion continues to propagate inward, gradually raising the temperatures in regions that have been cold for billions of years. The volatile ices that survived the journey through interstellar space may now be sublimating for the first time since their parent star system existed. What happens next will depend on factors we cannot fully predict: the composition of the nucleus, the distribution of volatiles, and the strength of the materials holding the object together. These factors vary greatly among solar system comets. And for interstellar visitors like 3 Atlas, they are completely unknown. The December 19th closest approach will serve as a crucible for testing these unknowns. If 3 Atlas emerges intact, it will have passed a test that destroys many comets far less exotic than itself. But if it fragments, it will join the growing list of objects that have underestimated the destructive power of the Sun. Either way, this observation will be historic. Either way, we will gain new knowledge about the universe and the wandering messengers that travel through it. 3I Atlas's passage through our solar system is a rare gift. It is a visitor from the darkness between stars, a cosmic wanderer whose journey we can observe. The clock is ticking, and the telescopes are poised to capture every moment of this extraordinary event. In just a few days, we will have our answer. But no matter what happens on December 19th, the story of 3 Atlas is far from over. In March of 2026, 3 Atlas will make its closest approach to Jupiter, the mighty king of the planets. That encounter may reveal even more about this enigmatic visitor, furthering our understanding of its composition and history. But for now, the December 19th window holds the promise of something truly extraordinary. On that day, 3 Atlas will reach its closest point to Earth. At 269 million kilometers away, it will be close enough to resolve details that have been invisible at greater distances. This rare opportunity will allow astronomers to measure spectra with unprecedented precision and answer questions that have been mounting since its discovery. The timing couldn't be better. The new moon will ensure the darkest skies possible for observers around the world. The lunar disk will be absent, leaving no light pollution to interfere with the faint glow of 3 Atlas. For those who want to observe the object with their own eyes, now is the time. It will rise in the east before midnight, climbing higher as the hours pass and reaching its most favorable position in the pre-dawn sky. For those at mid-northern latitudes, 3 Atlas will be more than 40 degrees above the horizon by 4 a.m., offering clear views free from atmospheric distortion. However, it's important to set expectations. 3 Atlas is currently shining at about 11th magnitude, which is too faint for the naked eye. Even under perfect conditions, objects fainter than 6th magnitude are difficult to see without a telescope. With a telescope of at least 30 centimeters, 12 inches in diameter, 3 Atlas will appear as a small, fuzzy patch with perhaps a slight elongation and a hint of condensation at the center. While it won't resemble the stunning images captured by Hubble or Webb, it will still be there. An actual photon traveling across the cosmos to reach your eye from an object that has journeyed across galaxies. The opportunity to observe 3 Atlas is rich with potential, especially for those with imaging equipment. Modern CMOS cameras can accumulate light over time, revealing details invisible to the human eye. Color information will emerge through stacked exposures, and structural features like the antitail, jets, and complex coma morphology will be captured, offering insights into this interstellar object that would otherwise remain hidden. The professional campaign for December 19th is vast, with more than 80 observers participating through the United Nations International Asteroid Warning Network, IAWN. This international effort underscores the scientific significance of 3 Atlas and the global cooperation that is vital to modern astronomy. The IAWN campaign, led by James Bauer, aims to refine the object's trajectory and publish comprehensive findings in a peer-reviewed journal next year. Data being collected includes precise astrometry to refine the trajectory, photometry to track brightness variations, and spectroscopy to analyze gas emissions. Each observation contributes to a growing database that will enable detailed modeling of 3 Atlas's properties. The Hubble Space Telescope has already delivered high-resolution images and plans additional observations during the closest approach window. Hubble's ability to resolve fine details will complement the work of the James Webb Space Telescope, which offers unparalleled infrared capabilities. Webb's instruments will measure thermal emissions, analyze the dust coma, and identify molecular species through their vibrational signatures. These observations will provide insights that optical telescopes simply cannot detect. Ground-based observatories, such as the Very Large Telescope in Chile, the Gemini telescopes in Hawaii and Chile, and the Gran Telescopio Canarias in the Canary Islands, have all contributed to this global campaign. Their efforts ensure that weather disruptions at one site don't interfere with the observation process. The comet is never out of sight for long, thanks to this global network of telescopes. Radio telescopes have also joined the campaign, providing a unique perspective. Radio observations can detect the O radical, which forms when solar ultraviolet radiation breaks apart water molecules in the coma. The intensity of the O emission offers an independent measure of water production rates, complementing optical and infrared data. Radio telescopes are also on the lookout for unusual signals that might suggest non-natural origins, though no such signals have yet been detected. As December 19th approaches, the observations will become even more focused on answering key scientific questions. The structural integrity of the nucleus will be tested as high-resolution images capture whether 3 Atlas remains a single body or shows signs of fragmentation. The antitail will be examined in detail, and spectroscopy will reveal the chemical composition of the coma, offering insights into the comet's internal processes and evolution. As we prepare for December 19th, the potential for 3 Atlas to reveal new, unprecedented behaviors becomes ever clearer. If fragmentation is on the horizon, we may first witness subtle signs, multiple condensations, asymmetric morphology, or fluctuations in brightness. These could all signal the comet's internal collapse. Second, the nature of its antitail will be scrutinized. At the closest approach, the extension of this sunward feature will be imaged in exquisite detail. Is it smooth? Or does it show intricate filaments? Is it coherent or diffuse? These characteristics will help us determine its origin, whether it's purely cometary or something altogether more mysterious. Some models suggest that if the antitail is composed of larger particles, it should exhibit different scattering properties than a dust tail made of smaller grains. Understanding these differences could lead us to fresh insights about the comet's composition and behavior. Third, the chemical composition of the coma will be a focal point. Spectroscopic data gathered at closest approach will offer the best signal-to-noise ratios of the entire observation period. This is our chance to detect trace species that have been invisible at greater distances, molecules that could unlock further secrets about the comet's volatile inventory and internal chemistry. The relative abundance of gases and how their concentrations change since perihelion will shed light on the ongoing thermal and chemical processes occurring within the nucleus. Understanding these changes is crucial to our understanding of 3 Atlas's internal activity. Fourth, the non-gravitational acceleration will continue to be a key parameter to monitor. As astronomers refine their astrometry, we'll be able to measure precisely how 3 Atlas's trajectory deviates from what gravity alone would predict. This will reveal the role of outgassing and any other forces at play in shaping its flight path. And then there's the possibility of encountering something entirely unexpected. After all, science is driven by surprises, and 3 Atlas has already delivered more than its fair share. The observing campaigns are designed not just to confirm existing theories, but to capture whatever anomalies might emerge. As December 19th draws closer, the geographical distribution of observers will play a crucial role. The object will be positioned high in the sky in the northern hemisphere, making it an ideal target for observation during the pre-dawn hours. For viewers in North America, the optimal time for observation will be between 3 and 5 a.m. local time on December 19th, with 3 Atlas located just beneath Regulus, the brightest star in Leo. This makes the comet relatively easy to locate using star charts or planetarium software. For European observers, the timing will shift earlier, and for those in Asia, the best window will occur between late evening and midnight, no matter where you are on Earth. If you can see Leo in the sky, you will have a chance to observe this interstellar guest. What should observers document if they successfully image 3A Atlas? Several aspects of the object are scientifically valuable, even from modest equipment. The overall brightness, determined through comparison with nearby stars of known magnitude, will add valuable data to the light curve database. The apparent size and shape of the coma, measured in arc seconds or arc minutes, will provide insights into the extent of visible activity. Any obvious structural features, such as jets or asymmetries, should also be recorded and reported. Contributions from amateur astronomers are not only welcomed but highly valued. The American Association of Variable Star Observers maintains a comet section where observations can be submitted in standard formats. And the International Astronomical Union's Central Bureau for Astronomical Telegrams publishes significant findings. Online communities such as Cloudy Nights and Ice in Space offer platforms to share images and discuss observations. This collaborative effort between professionals and amateurs ensures that 3 Atlas is thoroughly documented from every possible angle. The December 19th observation window is short in astronomical terms. Within a few days, 3E Atlas will begin to recede from Earth, and its coma will shrink in angular size, reducing opportunities for high-resolution observation. By January, the object will be significantly fainter, making it more challenging to observe. By February, only the largest professional telescopes will maintain meaningful contact. The closest approach is truly a critical moment, the best chance we will have to study this interstellar visitor before it departs for good. Even if your results are modest compared to professional imagery, there is value in the personal experience of observing 3 Atlas. When you peer through your telescope, you are connecting directly to something vast and ancient. The photons you detect left the surface of that comet approximately 15 minutes earlier, having traveled from the Sun to itself, a journey that took about 8 minutes. But 3 Atlas has traveled for billions of years, crossing unimaginable distances and passing through the territories of countless unknown stars. For a brief moment, our paths intersect. For a brief moment, we can reach out with our instruments and touch something that hails from another world. After December 19th, 3 Atlas will continue its journey, heading toward Jupiter and beyond, back into the vast darkness between the stars. We will watch it fade into the distance, analyzing the data it leaves behind, building models, and testing our hypotheses. But we will never see this particular visitor again. The universe is full of encounters like this, connections that flare briefly and then vanish into the cosmic night. Most of these objects go unnoticed, drifting through our solar system without any observer to mark their passage. 3 Atlas is different. It was caught, detected, tracked, and studied. It will not slip away unnoticed. If the observations reveal something unexpected, if the data forces us to reconsider our understanding of interstellar objects, December 19th, 2025, will be remembered as the day everything changed. This is a rare opportunity to reshape our understanding of the cosmos and to learn something truly groundbreaking about the universe and its wandering messengers. With the telescopes aligned and the observers ready, the countdown to the December 19th closest approach has begun. In just a few short days, 3 Atlas will reach perigee, its closest point to Earth. What we discover at this moment will be the next chapter in a story that has been unfolding since July. But even as we focus on this critical date, we must remember that the journey of 3 Atlas does not end with its closest approach to Earth. Another encounter awaits, one that could prove just as significant. In March 2026, 3 Atlas will make its closest approach to Jupiter, passing within 54 million kilometers of the giant planet. The gravitational influence of Jupiter may reveal aspects of the comet that remain hidden from our current vantage point. This upcoming passage holds the promise of further discoveries that will deepen our understanding of this interstellar traveler. We've spent hours examining the scientific evidence surrounding 3 Atlas, its color transformations, the strange anti-tail, its unusual chemical composition, and the 13 documented anomalies it exhibits have all prompted a careful and rigorous approach to understanding this object. We have treated it as any scientist should, a phenomenon to be carefully studied and explored without jumping to conclusions. But there is another conversation happening in parallel, one that has captivated millions of people around the world. This conversation has sparked viral social media posts, primetime news coverage, and debates in comment sections, podcasts, and dinner tables alike. It's a conversation that asks a question that science cannot definitively answer, but also cannot entirely dismiss. What if 3 Atlas is not a comet at all? What if it is something else, something constructed, something sent from another civilization? The leading voice in this conversation is Avi Loeb, the Frank Baird Jr., professor of science at Harvard University. Loeb is not a fringe figure. He has published hundreds of peer-reviewed papers and held leadership roles in major scientific institutions. Yet his suggestion that our first interstellar visitor, Oumuamua, might have been an artificial object, a light sail, or debris from another civilization, has raised eyebrows in the scientific community. Since then, Loeb has continued to champion the idea that 3 Atlas may share similar origins, prompting him to catalogue its anomalies and question whether they could point to technological origins rather than natural ones. Loeb's hypothesis, in its strongest form, proposes that 3 Atlas could be a spacecraft cleverly disguised as a comet. In this scenario, the cometary activity we've observed would not be the result of natural sublimation, but rather the effect of accumulated interstellar material coating an artificial core. The anti-tail might be thrust exhaust, and the comet's trajectory could be part of a deliberate navigation plan rather than a random chance. Loeb even suggests that the comet's timing, which brought it close to multiple planets while hiding it from Earth observation during perihelion, could indicate a planned reconnaissance mission. He has entertained the possibility of a dark forest scenario, a science fiction concept where 3 Atlas might be a potential threat, a probe sent to gather intelligence, or even a scout for a much larger mission. These ideas raise important questions about the nature of interstellar objects and their possible origins. While this hypothesis is intriguing, it is not the scientific consensus. The majority of astronomers studying 3 Atlas believe that it is a natural comet with unusual properties, but not artificial in origin. Agencies like NASA, ESA, and others have explicitly stated that 3 Atlas is a comet, and there is no immediate threat. Loeb's arguments remain speculative, with no direct evidence of artificial origins. However, Loeb's approach does bring valid points to the table. After all, we have detected only 3 interstellar objects in human history. We have no baseline for what typical interstellar objects should look like, and our models of cometary behavior are all based on solar system objects, formed under entirely different conditions. Extending these models to interstellar visitors is a leap of faith. The history of science is full of instances where unexpected phenomena reshaped our understanding of the universe pulsars. The cosmic microwave background. Black holes all were once considered anomalies before they were understood within the framework of conventional physics. Loeb's theory, while controversial, pushes us to think outside the box, challenging the assumptions that shape our scientific thinking. The specific anomalies Loeb has highlighted are not imagined. The trajectory alignment is real. The anti-tail is real. The unusual nickel chemistry and non-gravitational acceleration are also real. Each of these features requires an explanation. While natural explanations exist for each anomaly, the combination of so many unlikely features in a single object is statistically notable. Loeb has estimated a 30–40% probability that 3 Atlas is not fully natural in origin, with the remaining 60–70% assigned to the idea of an exotic, but natural comet. This probabilistic framework helps us reason about the unknowns, updating our beliefs based on accumulating evidence. Critics argue that Loeb may be overemphasizing the potential for technological origins, cautioning that natural explanations for all these anomalies remain plausible. They emphasize that extraordinary claims require extraordinary evidence, and that anomalies alone are not enough to justify such claims. These criticisms underscore the need for careful, grounded scientific inquiry, especially when it comes to extraordinary phenomena like 3 Atlas. The discourse surrounding 3 Atlas has been complicated by misinformation, with false claims about trajectory shifts and impending impacts circulating on social media. These distractions highlight the importance of careful, accurate observation, and of keeping the focus on the science rather than speculative sensationalism. Nonetheless, 3 Atlas has raised important questions that will continue to inspire investigation for years to come. In recent weeks, an astonishing 40% of social media posts about 3 Atlas have woven narratives about aliens or extraterrestrial technology. As revealed by an in-depth analysis, this surge of speculation is not directly the fault of Avi Loeb, but his prominent public statements have undeniably fueled imaginations far beyond the realm of scientific inquiry. Still, Should we shut down inquiries merely because they might be misused or misunderstood? No. Science must not shy away from asking bold and even uncomfortable questions, even those that might make colleagues raise an eyebrow. The history of astronomy is defined by its ability to expand the boundaries of the possible. For centuries, we've been uncovering the truths of the universe, revealing that it is far stranger and more diverse than we ever assumed. So, let's explore the technological hypothesis on its own merits. Let's allow the evidence to guide us, no matter where it leads. What would we expect if 3 Atlas were truly an artificial object? First, we'd anticipate its survival through the inner solar system without fragmentation. After all, technological artifacts are engineered for durability, designed to withstand the thermal stresses that often destroy natural comets. If 3 Atlas remains intact after passing closest to the Sun through December 19th and beyond, it would pass one of the major tests for an artificial origin, even as a naturally robust comet could do the same. Second, we would expect the non-gravitational acceleration to persist, even as outgassing decreases. Natural comets rely on volatile sublimation for acceleration, but that force should diminish as the comet moves away from the Sun. An artificial object, on the other hand, could rely on technological propulsion, which would continue independent of solar proximity. Over the coming months, tracking the acceleration profile will help us test this prediction. Third, if 3 Atlas were artificial, we would expect some form of unusual electromagnetic emissions. Technologies designed to run on power often leak detectable signals, radio waves. For instance, yet no artificial signals have been detected so far by our radio telescopes. While this is a negative result, it doesn't definitively rule out the possibility of technology, as sufficiently advanced systems could be entirely indistinguishable from natural phenomena. Fourth, as the comet continues its journey, we would expect the accumulated interstellar material to be slowly depleted, revealing whatever lies beneath. If 3 Atlas is artificial, this covering of icy material should eventually erode due to continuous solar heating, exposing the core beneath. To date, we haven't observed any such signs, but the time frame might extend beyond our current observation window. This slow process would unfold over many months, if not years. Alongside these expectations, the technological hypothesis also implies that we should not see certain behaviors. An artificial object should not fragment under normal conditions. It should not exhibit chaotic or random outbursts. The structure should remain intact and operational, without signs of failure or instability. Every observation of standard cometary behavior thus weighs against the technological hypothesis, while each anomaly, however small, adds circumstantial support to it. The scientific community's dismissal of the technological hypothesis is not arbitrary. It's rooted in the principle of parsimony. This principle dictates that we should prefer simpler explanations over more complex ones when both fit the data. A comet with unusual properties requires fewer assumptions than a spacecraft disguised as a comet. However, the burden of proof remains with the extraordinary claim. Yet, we must also recognize that parsimony is a guideline, not an ironclad rule. Sometimes, the complex explanation is correct. Sometimes, the simpler one fails to account for essential details. The aim of scientific observation is to distinguish between competing hypotheses and let the universe reveal which interpretation best captures reality. December 19th and the months following will provide us with ample opportunities to test the technological hypothesis. If 3 Atlas behaves exactly as we would expect a natural comet to behave, the technological hypothesis will lose support. However, if it continues to show anomalies that defy conventional explanation, that hypothesis will gain credibility. Either way, we will learn something profound. What Loeb has done, whether for better or worse, is provide a framework for thinking about observations that might otherwise be overlooked. By clearly articulating the technological hypothesis and specifying what evidence would support or refute it, he has created a testable proposition. This is the essence of scientific methodology, regardless of how controversial the proposition itself may be. Loeb's Galileo project. For instance, has deployed observatories to systematically scan for anomalous aerial phenomena and strange objects in Earth's atmosphere. 3 of these observatories, located in Massachusetts, Pennsylvania, and Nevada, will monitor the sky during the closest approach of 3 Atlas. If the object releases any probes or exhibits behavior detectable from Earth's surface, these instruments will be ready to capture it. This is science pushing the boundaries of what's considered mainstream, venturing into uncharted territories that many scientists hesitate to explore. Such work invites ridicule and skepticism, but it also invites the potential for discovery. We do not yet know what 3 Atlas truly is. Neither Loeb nor anyone else can claim absolute certainty. The data we've gathered narrows the possibilities, but we are still in a state of genuine uncertainty, which is both uncomfortable and honest. What I do know for sure is this 3 Atlas is extraordinary, no matter its origin. If it's a natural comet, it's showing us that interstellar objects can be far stranger than we ever expected. If it turns out to be something else, it's revealing that the universe holds possibilities we haven't even dared to consider. Either lesson is invaluable. Each discovery, each possibility expands our understanding of the cosmos. And, no matter the outcome, the mystery surrounding 3 Atlas will continue to unfold as we observe it through its closest approach toward Jupiter and its eventual departure from our solar system. The mothership hypothesis may ultimately prove to be nothing more than a modern myth, projected onto an ancient traveler. Or it could reveal something far more profound, a glimpse into a reality far beyond our comprehension. We won't know for sure until we look. And as we prepare for that next pivotal chapter, there's Jupiter, waiting at the outer edge of the inner solar system. In March 2026, 3E Atlas will pass within 54 million kilometers of the gas giant, and its gravitational influence may give us a closer, more refined look at the comet and its mysteries. What that encounter reveals could dramatically reshape our understanding of the object. The December 19th window is merely a milestone in this cosmic journey. After passing through the inner solar system, after surviving its perihelion with the Sun, and after transforming from red to green to gold, 3I Atlas has yet another significant appointment. March 16th, Unveiling will bring 3 Atlas within 54 million kilometers of Jupiter. This proximity will allow the giant planet's gravity to influence the comet's trajectory, and the observations made at this time could offer details that are currently beyond our reach. Jupiter is not just a planet, it is a gravitational powerhouse that has shaped the solar system for billions of years, its mass far exceeding that of all the other planets combined. For 3 Atlas, this encounter represents both a scientific opportunity and a potential turning point. The gravitational interaction will help refine our understanding of the object's mass and density, while the viewing geometry will provide unique angles for observations that are not possible from Earth. The passage through Jupiter's sphere of influence will test the structural integrity of 3 Atlas's nucleus, which has already been subjected to solar heating and other forces. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, remains operational and could be called upon to contribute valuable data. Though Juno's primary mission is focused on studying Jupiter itself, its instruments may be able to capture critical information about this interstellar visitor. Whether or not Juno will be tasked with observing 3 Atlas is still to be determined, but the possibility is unprecedented. If Juno is tasked with observing the comet, it could provide data that we simply cannot get from Earth-based telescopes. No spacecraft has ever been in such a position to study an interstellar object at close range. However, the passage through Jupiter's gravitational field brings its own set of challenges. Small uncertainties in the comet's exact trajectory or Jupiter's position could significantly alter the post-encounter trajectory, making future predictions more difficult. The gravitational perturbation from Jupiter could also add another layer of stress to the nucleus of 3I Atlas, already weakened by the intense heat from its perihelion. If the comet is on the verge of fragmentation, this encounter could push it over the edge. Conversely, if 3 Atlas survives the encounter intact, it will have passed every conceivable test our solar system can throw at it. After the Jupiter encounter, 3E Atlas will continue its journey into the outer reaches of the solar system. It will cross the orbits of Saturn, Uranus, and Neptune, gradually fading from view as it moves farther from the Sun. By the early 2030 seconds, it will have entered the Kuiper Belt, leaving behind the planetary region of the solar system and entering the vast, cold expanse of the outer solar system. Eventually, it will pass through the Oort Cloud, the distant spherical shell of dormant comets that marks the outermost reaches of our Sun's gravitational influence. After that, it will disappear into the darkness of interstellar space, continuing its journey toward destinations we cannot yet predict. Where will 3 Atlas go next? Its trajectory, altered by gravitational encounters, will likely lead it toward another star system, but no one knows which one. It could travel for millions, perhaps billions of years, passing through countless stellar neighborhoods without ever being detected, a silent wanderer in the cosmic void. Or perhaps, just perhaps, it will eventually encounter another world, one with observers who will notice its passing. If 3 Atlas is a natural comet, those future observers will see the ancient, weathered remains of a celestial traveler, carrying the chemical fingerprints of its long journey across the stars. If it is something else, they may encounter something we fail to recognize. This thought is both humbling and awe-inspiring. We are not the first to observe this object. Stars have been born and died during its journey. Civilizations may have risen and fallen on worlds we will never know. 3 Atlas's story spans far longer than humanity's. It may have been traveling long before the birth of Earth, perhaps even before our sun was formed. Yet, here we are, at this moment, standing in awe with our telescopes and spectrometers, trying to decode the message written in photons that have traveled across vast distances and ages. This is the beauty of science. It bridges distances, transcends time, and transforms the unknown into something we can understand. And when that understanding proves elusive, science remains vigilant, watching, recording, and waiting for the next piece of evidence to reveal a clearer picture. 3 Atlas has been a remarkable teacher these past few months. It has shown us that interstellar objects can be large, active, and complex, revealing chemistry unlike anything we've seen in solar system comets. Its anomalies have pushed the boundaries of our knowledge, forcing us to rethink what we thought we knew about the cosmos. The December 19th closest approach will mark the pinnacle of this chapter in the story of 3 Atlas. But this is only the beginning. The data we collect will be analyzed for months and years to come, with papers published and debated. As our understanding deepens, we will look back at this moment as the time when we first truly understood interstellar visitors, or perhaps the moment we glimpsed something beyond our comprehension. I cannot say for sure which it will be. None of us can. The universe keeps its secrets until we've earned the right to uncover them through patient observation and rigorous analysis. But tonight, somewhere on Earth, an astronomer is preparing their telescope, aligning the optics, cooling the camera, consulting star charts, and waiting for the moment 3E Atlas rises above the horizon. When the clock strikes and the object is visible in the sky, they will open the shutter and begin capturing light. The photons they catch will have traveled for 15 minutes from the surface of 3 Atlas. But the story they carry, that's billions of years old, a journey across stars, a story written in nickel, cyanide, diatomic carbon, and organic molecules, accumulated over eons. We are privileged to be the ones reading it. Thank you for joining me on this extraordinary journey through the mysteries of 3 Atlas. Together, we've uncovered layers of this enigma, whether it's the golden transformation, the mysterious anti-tail, or the question of its true origin. Each of these anomalies opens new doors, pushing the boundaries of our knowledge further than we could have imagined. The December 19th observation window is nearly upon us. If you're able, I encourage you to look up, find Leo, locate Regulus, and watch for that faint, fuzzy patch in the sky. That is 3E Atlas, an ancient messenger from another star, traveling through the cosmos. And for this fleeting moment, within reach of our instruments and our curiosity, the truth is, I don't know which conclusion we'll come to. I don't think anyone truly does. The universe holds its secrets close, allowing us only glimpses when we earn them through patient observation, careful measurement, and rigorous analysis. But what I do know is this tonight. Somewhere across the globe, an astronomer is preparing their telescope, fine-tuning the optics, adjusting the camera settings, and poring over star charts to pinpoint the exact position of 3 Atlas in the vast constellation of Leo. And as the clock ticks closer to the appointed time, when the interstellar visitor rises over the horizon, they'll open the shutter, letting the light pour in. These photons, tiny packets of light, will have traveled for 15 minutes from the surface of 3 Atlas. But the journey they represent spans billions of years. What they carry is a tale written in the very building blocks of the cosmos: nickel, cyanide, diatomic carbon, water ice, and the dust of organic molecules, each one accumulating during the longest and most remarkable journey we could ever imagine. We are incredibly fortunate to be the ones who get to read this story. As we near the conclusion of tonight's deep dive into the mysteries of 3 Atlas, I want to express my gratitude for your time, for joining me on this journey into the unknown. We've explored a vast expanse of cosmic wonder, from the transformation of the object into gold, to the sunward jet, the puzzling nickel anomaly, and the bold mothership hypothesis. We've uncovered 13 anomalies, each one raising more questions than answers. With the help of X-ray telescopes, we've peered deeper into the object's heart and contemplated the ticking of the fragmentation clock, unsure if it's counting down to disaster or a deeper revelation. Through it all, 3 Atlas has remained as mysterious and captivating as it was when we first detected its presence in July, a cosmic enigma, wrapped in a coma of gas and dust, traveling along a trajectory through our solar system that has been unfolding for far longer than our species has walked the Earth. The December 19th observation window is just 3 days away. If you have the equipment and the curiosity, I encourage you to look up, find Leo in the pre-dawn sky, locate Regulus, the brightest star in the constellation, and just below it, you might spot a faint, fuzzy patch. At first, you might mistake it for a distant galaxy, or perhaps think your eyepiece is smudged. That's 3 Atlas, a visitor from another star, crossing through our corner of the galaxy. For this brief, precious moment, it's close enough to touch with light, an object from beyond the stars, traveling across the void, passing through our solar system. Whatever your personal conclusions about its nature, whatever hypothesis you find most compelling, take a moment to pause and appreciate the sheer improbability of this encounter. Consider the incredible sequence of events that had to align for this moment to happen. An object had to form around another star, distant and foreign to us. It had to be ejected into the great expanse of interstellar space, drifting for billions of years. It had to follow a trajectory that would bring it into our solar system, into the tiny sliver of time when a species arose on Earth, capable of detecting and studying it. All these conditions had to come together perfectly, and they did. We are fortunate, beyond measure, to be here for this. We are lucky to witness this cosmic moment, and we're fortunate to be part of a global community of observers, scientists, dreamers, and explorers, united in our quest to understand the universe and our place within it. Thank you for watching, for listening, and for caring about this tiny speck of light moving across the cosmic tapestry. If this exploration of 3 Atlas has resonated with you, if you've enjoyed delving into its mysteries, please consider giving this video a like. Your support means more than you might realize. And if you haven't yet subscribed, now would be the perfect time to join our growing community of curious minds, all exploring the wonders of the cosmos together. As always, the information presented here is based on the best available scientific understanding. But it's important to note that as new data comes in, our conclusions may evolve. I urge you to stay engaged with the ongoing observations, to read the research papers as they're published, and to form your own conclusions based on solid evidence rather than speculation. The sky above us is vast and infinite, and the universe is ancient. Every night, if we choose to look, there are wonders waiting to be discovered. Good night, my friends, and thank you for being part of this incredible journey.